Just something you throw off the back of a train. Got a head full of lightning, head full of rain, and I know that I said never do it again. Oh, when I love you, sweet baby, I always take a long way. I put food on the table and a roof over head, but I traded all of my highway instead. Watch your back if I should tell. Love's the only thing I ever knew. One thing's for sure, sweet baby, I always take a long way.
Tim warned me about those lights.
Oh, they're bright. It's like right in your eyes.
I know, he
It's gonna
said,
be hard to
oh,
see."
be careful with those lights, they're awful.
How are you?
Yeah, good. Better today.
Better today.
Yes. I mean, I have no jet lag, so I cannot complain. How are you?
Monday or Tuesday. I got here Tuesday morning, so
Oh.
Tuesday.
Oh,
Tuesday was pretty tiring. Yeah, I came. Yeah, I landed at 7 in the morning.
do you want some water?
Yeah, that would be great. Thank you. So Tuesday was pretty tiring, and yesterday I had work I had to do, so I worked most of the time.
Oh, no. Had to run from the station, so I'm like. So will we introduce ourselves? I think. Each one says their name and affiliation, right? Because I've seen the one says both names and affiliations. I thought it's better if everyone.
Sounds good. Four more minutes.
4?
Yeah. 4 more minutes.
Oh my phone, my God.
Gotta watch that.
I didn't charge it. That's gone.
Yeah, we have 4 minutes. Seems pretty simple though. Seems like they've got it all organized pretty well.
Oh, they are so awesome.
Yeah,
Yes.
this is awesome.
They've been running around and like they have everything organized to they align the speakers, they do the changes. We have to do nothing, sit down and sort of like smile. Yeah. And the clock keeps them in time, so we have to do literally nothing.
Even the video runs, right? So it's like they have
Yeah,
to
they
stay on
have
time.
to start. Yeah. Like sometimes doesn't start right away. That's the only.
Yeah.
But otherwise,
The only thing we could do wrong is introduce them really slow.
I messed up the time.
That's the
Yeah.
only thing we could do.
So I think we can be efficient. Oh, new title. Okay, so let me read my TSDF. Show your shine. I can do that.
Yeah, so this one's also new.
have very long names in this session. Like now with all the suggestions from ChatGPT, it's always not to the color.
It's like short name, colon. And this one's got a dash.
Yeah. Yeah, that's the favorite. I'm glad someone has a watch. I'm just showing off here. Forgot to charge it last night. I expected that the 9 a.m. session will be not very packed.
Yeah. First thing in the day, right?
Yes. Okay, I think Lucas is preparing.
Yeah. You want to start?
Yes. Welcome everyone to the Perception and Estimation session. I'm Teresa Vidal Caleja from the University of Technology, Sydney.
And I'm Joshua Mangelson from Brigham Young University. And we will get started. So our first talk is Free Occ, Training Free Embodied Open Vocabulary Occupancy Prediction, presented by Zheyu Zhang.
May I start?
Yes.
Oh. Hello, everyone. I'm Zhang Zeyu. I'm very happy to present our work, Free OCC, Training Free Embodied Open Vocabulary Occupancy Prediction. 3D scene understanding is fundamental for embodied agents to represent 3D scene. Existing methods typically use explicit representation, such as point clouds and meshes, or implicit representation, such as nerves and Gaussian splatting. In this work, we focus on occupancy as unified and compact scenes representations. Current, most embodied occupancy works are closed-set learning-based methods, where they focus on incremental reconstruction of the entire room. On the right, legal OCC achieves open-set occupancy prediction, but it still requires supervised learning with geometric label. So the question is why we need a training-free pipeline. Learning-based methods need large-scale manual labels for geometry and semantics. As shown on the right, learning-based methods perform poorly when applying to an unseen environment. Free OCC is the first training-free open vocabulary occupancy prediction method. There are two main contributions of Free OCC pipeline. First, it incrementally constructs a globally consistent occupancy map through a 4-stage mapping pipeline. Second, we introduce a novel Gaussian update strategy that produces dense and spatially consistent Gaussians, overcoming the geometry ambiguity of rendering-oriented 3D Gaussian representations. Next, let me walk through the overall design of Free OCC. A SLAM backbone processes monocular or RGBD image sequence to estimate camera poses and build sparse point cloud maps. We encode Gaussian center to SLAM point and initialize their shapes along viewing range, producing dense Gaussian map with less ambiguity during optimization. Open vocabulary semantic features from pre-trained VLMs are incrementally linked to Gaussian primitives, enabling language-based query without voxel-level supervision. A probabilistic Gaussian to occupancy projection aggregates geometric and semantic cues into discrete voxel grid, producing a dense occupancy map with open vocabulary semantics. Then, the agent can perform online queries on open vocabulary occupancy. We evaluate our methods on embodied OCC scannet and use IOU as metrics. We choose fully and self-supervised methods as baseline. Our methods has outperformed self-supervised method. However, the fully supervised method uses scannet as the benchmark both for training and evaluation. In order to test the generalization performance on unseen environment, we create replica OCC, a small and test-only benchmark. The IOU results are shown in the table. Learning-based methods have failed almost entirely on replica OCC. Free OCC outperform all learning-based methods by a large margin. The ablation result further validate our Gaussian update strategy, improve both geometric accuracy and efficiency. Finally, we present the visualization result of our system's multi-layer map and real-world result from RealSense RGBD camera. If you have any question, please feel free to discuss with us during the poster season, and thank you.
Okay, our next paper is More with Less, Local Scene Representations for Tactile Imaging, presented by Zohar Riemann.
Yeah. Hello, my name is Zohar, and I'm going to present our work on tactile imaging. We present the first ever 3D data-driven handheld tactile imaging system. As you can see here, by pressing on a soft object with our tactile sensor, we're able to reconstruct the inner model of the object. Now, touch sensing is very important for a variety of applications in robotics as well as medicine, where, for example, palpation, the use of touch in medical examination, is very important for early breast cancer detection. But touch understanding is very difficult if you think about it. For example, here we have our soft object where everything is deformable, so touching it creates very complex force sequences. But our insight is that doctors don't learn to understand touch in medical school. They do so during their childhood by playing with different toys randomly and exploring the environment. So we follow a similar approach and design a modular soft phantom. We generate thousands of different configurations of it and let the robot touch it for 800 hours, creating the largest such dataset to date. Now that we have this diverse dataset, we can use it to learn to extract relevant patterns in the touch sequence. We do so, obviously, with self-supervised learning. We basically just reconstruct forces at unseen positions within the touch sequence. But we have a big problem. What if we want to work on a general object, say with one inclusion, multiple inclusions, and different shapes and sizes? Do we really need to create all of the different configurations? That's not really scalable, right? But our saving grace is that touch is a local sensation. Basically, a measurement from one side of the model doesn't tell us much about the other side of the model. We can leverage this to our advantage and compose the scene from local touch representations. The way we do that is by spreading particles on top of the relevant area, each with a small receptive field of 1 centimeter, and then we employ the same sequential RNN centered at each particle, but reconstructing forces only within each receptive field. What we get is a very, then we take our models to an MRI machine to create the tactile image, to extract the tactile image. So we get from an MRI the ground truth 3D model. But then to preserve the locality of our model, instead of just predicting the image at one go, we predict a local patch from each particle with an overlap between the patches. Then what we get is a very accurate 3D reconstruction. As we get more measurements from the model, our prediction improves. But the cool part, although our model only saw models with single inclusions during training, we're able to reconstruct multiple inclusions. That's because multiple inclusions are essentially a composition of single inclusions. And same goes for phantoms of different sizes, objects of different shapes. Here, for example, we only trained on the phantom on the right of a fixed size, and we're able to generalize zero shot to a phantom of a larger size, here 4 times as large. As we saw before, we're also able to generalize to handheld motions although our model trained on robot motions, and we achieve a very accurate handheld tactile imaging system. To conclude, most works have focused on, in tactile sensing, focused on manipulation. But here we're trying to get to real touch understanding. But there are a lot of open problems. That's a tough one. So if you found this interesting, we released everything, including data and code. So please reach out. And also come by our poster, because we have a live demo of the handheld system. Thank you for listening.
Our next talk is Annie Amber, a generalist for versatile anonymous bearing and range-based position tracking by Si Wang.
Hey, good morning, everyone. I'm Si Wang from Zhejiang University. Today, I'm so glad to introduce our paper, Annie Amber, a generalist position tracking network. Position tracking based on bearing and UWB ranging is widely used in robotic navigation tasks. However, due to the variations in the number of robots, anchor and tag layouts, visual anonymous bearings, existing methods typically rely on task-specific architectures, limiting their usability and generalization. So in this paper, we introduce a unified learnable model, enable joint pre-training and data-efficient fine-tuning. So to achieve this, we require two key components, unified problem formulation and high-fidelity measurements. Specifically, build upon the unified reference frame formulation, a heterogeneous EGAT aggregates multi-sensor geometry to accurately estimate pose and covariance. To associate anonymous bearings with robots, we combine temporal graph attention with multi-frame synchron for differentiable matching. And to compensate for disturbances in UWB signals, a sensor-embedded GIU is employed for adaptive ranging calibration. We develop a comprehensive data set comprising both simulation and real-world scenes. Our data set covers varying number of robots, anchors, tags, as well as diverse trajectories and environments. We change of the baseline using as much corresponding data as possible. By contrast, our pre-trained model is fine-tuned in each test scene using only one trajectory. And the result shows that our model not only generalizes well across multiple tasks, but also achieves optimal or near-optimal performance. For single robot localization, Annie Amber outperforms all learning-based and optimization-based methods owing to the strong foundation. In the challenging GPS-denied tunnel flight test, the estimated trajectory of Annie Amber closely followed the green ground truth, while the trajectories of PGO and Unreal exhibit greater drift. And in real-world multi-robot scenarios, although the UWB ranging and bearing signals are partially encoded by bosses and human bodies, our estimations still match well with the ground truth, demonstrating strong robustness. We further evaluate the filtering and error correction in real-world scenes. By incorporating UWB sensor embeddings, the embedded GIU achieves superior adaptive ranging calibration than vanilla GIU. For data association, we evaluate different matching strategies across varying robot scales. The compact approach incorporates temporal information to be jointly optimized into a single score matrix. And for a trade-off between efficiency and accuracy, 100 iterations are employed in our final setup. To further investigate the functionality of each submodule and measurements, we conduct Bayesian studies on architectural configurations and different sensor inputs. And last but not least, we test generalization on fine-tuned trajectory numbers and robot counts. Fine-tune on only one trajectory, the pre-trained model outperforms the non-pre-trained model fine-tune on 5. Across robot counts, the mixed training generalizes best. And thanks for watching, and feel free to ask me questions at the poster session. Thank you.
Our next talk is motion-aware event suppression for event cameras, and it'll be presented by Roberto Pellerito.
So, hi everyone. So I'm Roberto from Robotics and Perception Group. Today I will present my work on motion-aware event suppression, so for event cameras. First, what is an event camera? So event camera is a sensor that reacts to the relative motion in the scene, as you can see here. So suppose now you have a rotating disc. With a standard frame-based camera, you capture frames at constant intervals. Instead, the event camera captures this continuous trajectory that you see on the screen. Now the disc will stop, and basically once it stops, like here, you have no events because you have no motion. Now, as you will see shortly, the disc starts to spin faster and faster. And what you see in the frame-based camera is that you have motion blur. In the event camera, you still capture this continuous trajectory. But here, the camera is fixed. What happens in case the camera starts to move? So all the points in the scene trigger events at the same time and in the same way, regardless if they are from the background or from the independently moving objects. Ideally, we want to separate the two sources. So we want to separate to recognize which pixels are from independently moving objects and which pixels are from the static background. Now, suppose that you use state-of-art approaches. So you need depth estimations, lamp poses, and optical flow. Still, you are as brittle as you can see here in the screen. And moreover, they take so much time that once you produce the mask, the object has already significantly moved in the screen. So we try to solve this problem by anticipating where the object will be in the next frame. So we take a stream of events, as you can see here. Then we take this stream of events and we convert into a dense-like representation, an image-like representation as in the screen. We encode and decode this representation to get an independently moving object mask. Then we take the features, we modulate them according to a certain target timestamp, and we get the future optical flow, let's say in the next 100 milliseconds. Now we warp the original mask to forecast the mask of independently moving objects in the future. Now this mask aligns perfectly with the incoming events. Essentially, we anticipate where the object would be. Now, we test on one benchmark, Vimo benchmark, which is basically an indoor scene with these objects moving with these nonlinear motions. What we demonstrate is that we can be around 70% better in terms of performances compared to the state-of-art approaches, 50% faster, and our algorithm roughly runs at 200 Hertz, so it's significantly real time. So what I'm showing here in the screen, the yellow part is the mask for independently moving objects. The rest is just an event representation. So blue for negative events, red for positive events. So our mask remains stable also in case of, let's say, these nonlinear motions. Now, we test also on different settings. So for instance, on the autonomous drive settings, as you saw at the beginning of the presentation, where the independently moving objects right now are just a small part of the scene, so these moving cars. Still, we're able to generalize in also this context. And we also apply our network to downstream tasks, like simplifying the segmentation problem by reducing the number of tokens that we give to a segmentation model, for instance, a VIT model. We increase by 10 FPS with minimal loss in accuracy. So if you are interested, you can check out our code. Everything is open. So scan the QR code or approach me on the poster session. So thank you.
Okay, our next talk is From Local Matches to Global Matches, Masks, Template-Guided Instance Detection and Segmentation in Open World Scenes by Yu Zhang.
So I'm going to present our work from local matches to global masks, template-guided incident detection and segmentation in open world scenes. This is a work done by my students in the Intelligent Robotics and Vision Lab at UT Dallas. So let's consider the following problem. A robot is asked to search or target objects in a cluttered scene. So in this example, we hope the robot can detect this computer chip. So our goal to input target image, input cluttered scene image and detect target objects. A straightforward way is to use language to specify target objects, such as red apple. Then we can leverage vision language models. However, there are many objects you cannot specify with languages, such as industry objects or this one. So our goal is to use template images and detect and segment the objects from clustered things. Previous methods of template-based detection, they leverage the object proposals, then compare the object proposals to a query image. There are several limitations. First, it highly depends on proposal quality, and they cannot handle occlusion very well. They don't use local queues very well. So in this work, we propose L2G detect. Given a set of template images and a clustered scene image, we have several stages of the method. First, we do some local patch level matching, so we can detect some key points on the objects. Definitely, there's some noises, so we do some candidate key point selection to get rid of this noise. Then we use the augmented SAM module to segment the objects. So now let's take a look at each component one by one. So in the local patch level matching, we leverage DynaV3 to compute patch tokens for both the template image and the query image. So we match these tokens using cosine similarity. So in this way, we can detect some key points on the target objects. But you can see there's some noises on the background or the other similar objects. So we have a second stage, which is to select the high confidence key points. So in this candidate selection stage, for each point, we leverage SAM to get a local mask. We use the point as a prompt in SAM module. Then we compute some candidate embeddings for each local mask. Similarly, we do the same thing for the template image, so we can get a template embedding. Then we compare the candidate embeddings to get a high confidence key points. So in this way, we can get most of the point on the target objects. So now let's see how can we do the final detection. Again, we leverage SAM, but we augmented it. You know, SAM is a prompt-based segmentation. We use points as a prompt, but more importantly, we introduce an object token memory where we have an object token for each object. It's a continuous learning setting, so we can keep adding object tokens into memory, and we train these object tokens with synthetic data. So finally, we get the segmentations. We have done experiments on 2 benchmarks for template-based object detection and segmentation. So you can see our approach outperformed previous methods by a large margin. On the left, it is more than 12% for average precision. Here are some quantitative examples. On the left, you see the template images. So we show the ground truth detection, one previous state-of-the-art method needs net, and our detection results. But more importantly, we can apply this approach to real robots. So you can see in our lab, we have a fetch robot, which is moving around, looking at objects in order to search these target objects. These template images are shown on the bottom right. So you can see some key point detection in the images. Once the target object is detected, it will indicate the user the object is founded. So to conclude, we introduced this approach based on local queues. It's proposal-free, leverage DynaV3 for key points. We have this instance-specific tokens. We can keep adding tokens into the memory. We have very good performance on benchmarks and real world. Please find me at my poster session. Thank you.
Our sixth talk is TESDF, Tetra-Encoded Sign Distance Field for Memory-Efficient and Accurate Collision Detection, presented by Harim G.
Good morning, I'm Harim G. Today I will represent Tetra-Encoded Sign Distance Field for Memory-Efficient and Accurate Collision Detection. In simulations, sign distance field, in short SDF, has been used for robust collision detection between complex geometries. There has been much research on how to express and use SDF for collision detection. Expressing SDF is all about how to divide the volume of the geometry and what local evaluation to use. For example, dense voxel SDF divide the volume with uniform voxels and uses local linear functions to express the SDF. This expression is simple and fast, but it becomes memory heavy for complex geometries. This can be elevated by using sparse grids or using polynomials and neural nets. But these require tree traversals and network inference, making SDF queries expensive and still inaccurate. Moreover, all of these representations cannot handle deforming geometries. In this work, we propose TSDF, a new representation that is memory efficient, guaranteed to be accurate, and deformable. We also build a GPU-based collision detection based on TSDF and integrate it with our GPU simulation. There are two key ideas for TSDF regarding dividing the volume and designing the local evaluation. The first is to use tetramesh to divide the geometry. Tetramesh inherently provides an adaptive division of the volume, leading to efficient memory use. We can also divide the crucial outer region selectively, such as the Boole's thread. Second, we use distance functions as local evaluations. Exact SDF can be obtained with a few point-to-triangle distance evaluation. Consider this 2D projected cross-shaped geometry, so faces become lines and tetrahedra become triangles. When evaluating SDF for any point in tetrahedron 7, for example, we can do this by finding point-to-triangle distances for the faces in the set E7. Moreover, this local evaluation can be done cooperatively within a GPU warp, a 32-thread cluster, further exploiting the GPU parallelism. So, if we have this kind of encoded face set for every tetra, we can evaluate the exact SDF efficiently for any query. Based on TSDF, GPU-based collision detection can be done like this. First, we find every triangle to tetrahedron overlapping region with a GPU broad face. Then we solve these optimization problems with Frank-Wolf for the overlapping regions. Here, instead of knife thread-wise parallel, which may cause register spill, we allocate GPU warp for each optimization problem. We compare collision detection accuracy and memory efficiency between TSDF and dense voxel SDF. Here, TSDF can satisfy tight tolerance requirements with much less memory. We also check deformability. We encode TSDF using the gripper mesh and give a large deformation. As you can see, we get the true SDF value for near-surface regions, even under large deformations without any re-encoding. Finally, we test our collision detection in challenging cases, such as real-time assembly tasks involving multiple complex parts. We achieve about a millisecond of compute time for 100,000 narrow face queries, while representing the entire scene in megabytes of memory. Thank you for listening, and come see my poster for more discussions.
Our next paper is Vision as LS, Safe Perception-Based Control from Learned Visual Representations via System-Level Synthesis, presented by Shuju Chan.
Good morning, everyone. It's my pleasure to present our work, Vision SLS. Safety is critical in real-world robot deployment. However, robot planning and control is subject to imperfect dynamics models and noisy sensors. A drone may be drifted by wind and leading to undesirable collisions. The related robust output feedback control problem is challenging because of the high-dimensional sensor input, error propagation for both dynamics and observation errors, and optimization over an infinite-dimensional space of policies. Previous works either lack scalability to high-dimensional robot systems or are not certifiable. Hence, a scalable, safe perception-based control framework is needed. We focus on vision-based tasks and have a threefold contribution, including a new formulation of robust nonlinear output feedback control problem, control-relevant feature reduction, and an efficient solver. To achieve robust constraint satisfaction and scale to high-dimensional systems, we build upon system-level synthesis, which constructs a nominal state and input trajectory and tracking feedback controller. In particular, this controller is derived by some intermediate variables, which also define switchable tubes. These tubes are used to tighten constraints, so the closed-loop rollouts using sensor measurements gathered online will remain safe under dynamics and perception errors. To reduce the dimension of image observations, we train a neural network to map dynovative features to a lower dimension and a linear observation function to approximate the complex reduction. The singular value of the observability matrix is included to extract control-relevant features. Then, we fit a polynomial to over-approximate the induced perception error, which is used to bound the observation error in the SLS problem shown in the previous page. To further reduce the solve time, we designed a sequential convex programming-based solver with two novel parallelized Riccati recursions as a subroutine, which compute the intermediate variables for the controller and the reachable tubes. This significantly speeds up policy optimization, making our method practical for robotics problems. In this experiment, a car needs to navigate to a goal region using overhead camera with an occluded area where the perception accuracy is degraded as shown in the heat map. Here, we compare with two baselines, certainty equivalent and non-robust. The certainty equivalent baseline leads to larger total tube size and thus accumulates more uncertainty. The non-robust baseline may collide with obstacles. In contrast, our method avoids directly traversing the occluded region to reduce the perception error since the tube size is penalizing the objective function. It also robustly avoids collisions since we explicitly consider errors during policy optimization. In the backflip experiment, the humanoid needs to track a backflip trajectory with partial sensing. This is a challenging high-dimensional task with 60 states. The closed-loop rollouts lie in the tubes, while the open-loop rollout do not, leading to unnatural landing poses and large joint angles, which may damage the robot. To the best of our knowledge, our method is the first to synthesize a certified output feedback policy for a system of this dimension. In the hardware experiment, a turtlebot needs to navigate in an office area. As shown in the right video, the rollouts of the turtlebot lie in the computed tubes, which indicates that our method is effective in reality. In conclusion, we solve safe perception-based control problem by formulating a novel optimization problem with SLS, extracting control-relevant features, calibrating perception error, and implementing an efficient solver. Thanks for listening, and looking forward to talk with you at the poster session.
Our next paper is Picasso, Holistic Scene Reconstruction with Physics Constraint Sampling, presented by Lorenzo Shajkevitz.
Hi folks, I'm Lorenzo and I'm presenting Picasso, which is about scene reconstruction under physics constraints on behalf of my co-author, Jimmy. So suppose you have this scene, you want to pick up one of the blocks without disturbing the marker. Which do you pick up? The obvious solution might be to throw this into a geometric reconstruction pipeline like SAM3D. Here's what it looks like. It's not very good. Objects are penetrating each other. Some are floating. We can put this in a simulation like Majoku and it just falls over. This problem extends beyond SAM3D. Other estimators like Foundation Pose have this issue, and it's really a problem in contact-rich settings where we want to do manipulation. So the goal of Picasso is to find physically plausible scene reconstructions. And we do this by enforcing physics constraints. In particular, we have 4 constraints. This free space penetration says we don't want the object penetrating the depth map from the camera. Then we have object-object penetration, object-environment penetration, and then this contact constraint says we don't want any floating objects. So these 4 constraints we can take, and then we have inputs, which are RGB image of the scene, a depth and masks of the objects we're interested in, and we can plug this into a standard reconstruction likelihood. The only difference from something like SAM3D is it's constrained to be physical. The nice part about this is it gives accurate reconstructions. We'll call this the Picasso reconstruction. But I'm hiding the fact that it's a pretty hard problem to solve. In particular, it's high dimensional. We have to estimate a bunch of different shapes and poses. The constraints are also combinatorial because we need to compare every pair of objects for this inter-object penetration. And then, as we'll see on the next slide, there's bad local minima that make this problem particularly hard to solve. So the insight and magic of Picasso is we solve this with sampling. In particular, we use a coarse-to-fine global sampling procedure. So, we're going to sample poses, shapes, and scales. Like here's 2 examples. Then we're going to compute the geometric reconstruction likelihood. So in these examples, the geometric reconstruction likelihood is about the same, but you can tell this one on the bottom really isn't very good. So the last step is we're going to use physics constraints to check whether or not the thing should be refined on. So then the goal in Picasso, we're just going to iteratively refine along the most promising estimates. And the nice part is we can do this in parallel using something like a GPU, and it's pretty fast and efficient. So I still haven't addressed the 2 problems. This combinatorial constraints, we have to check every pair of objects. We do this by just checking contact using a vision model. So now I can look at this scene, and I can see that the mug is in contact with the coffee, which is in contact with the clamp, which is in contact with the table, etc.
We're going to build this contact scene graph, so-called, and then we're going to work from the bottom to the top using the same sampling procedure. To address high dimensionality, we're just going to outsource shape estimation to something that uses a generative model that's pre-trained on a lot of data and gives us some candidates that we can then choose from. That's Picasso. Okay, so let's return to this scene. Which object should you pick up? Well, if we use Picasso to estimate the scene, we get a really nice reconstruction, and we can try picking up this leftmost block, and you can see that it causes the marker to fall. But if we get the middle one, the marker's fine. So indeed, if we do this in reality, moving the middle one, the marker's just fine. The last thing I want to mention is this Picasso data set. So we also released this data set of 10 real-world challenging contact-rich scenes. There's high-quality 3D annotations, and we're really excited to see how the community does on it. In summary, this has been Picasso. Picasso outperforms other geometric reconstruction estimators by using physics, and we solved this physics-constrained problem with sampling. We also released the Picasso dataset. We're really excited to see how you do. Thank you.
Our next paper is Simulation-Ready Clutter Scene Estimation via Physics-Aware Joint Shape and Pose Estimation, presented by Wenzhen Yuan.
Hi everyone, I'm Wenzhen Yuan from UIUC, and I'm going to present our work in collaboration with University of Hong Kong and Meta Reality Labs. New Vision Foundation models show great promise in estimating 3D shapes from a single RGB image. However, they do not appreciate physical consistency. When we place an estimated scene into a simulator, the scene just blows up immediately. Our new framework addresses the problem of simulation-ready clutter scene estimation. From a single image, we produce a multi-object scene that is physically consistent. And when our scene is imported into a simulator, the scene remains stable for long term. And the generated scene can be used for manipulation planning, policy learning, and policy evaluation. So how does our method work? We introduce a numerical optimization in the joint shape pose space. We encode visual matching as objective and enforce physics as constraint. Hence, we leverage two technical contributions. First, in terms of visual supervision, we represent objects as unions of convex holes. The geometry representation is compatible with many robotic simulators while remaining flexible to represent diverse shapes. In terms of objective, for the visible part, we encode ICP-like correspondence matching. Meanwhile, clutter scenes and single view will lead to heavy occlusions. Therefore, we enforce a transfer regularization with the strong shape prior provided the foundation models for the complete shape. Second, we introduce content reasoning using a separating hyperplane-based content model. This is enabled by the shape representation we select. For each of the hole pairs, we maintain additional separating hyperplanes as collision proxies, and we utilize the recent incremental potential contact framework. The contact model and induced contact forces are globally differentiable with respect to pose and shape parameters. With this, we can list physical constraints that produce simulation-ready results. For clutter scenes, we require each object to be in force-torque equilibrium, and the frictional forces should lie in the friction zone to prevent slipping. We solved this optimization problem using the augmented Lagrangian method. Despite the high dimensionality of the optimization problem, we discovered that there are structures like low-rank factorization and collision pairwise sparsity in the constraint Hessian. Therefore, we write our own customized solver, and that allows us to optimize thousands of vertices and forces on a single CPU. Now, let me go through a more detailed illustration with the representative scene that contains occlusions, inclined objects, and complex support relationship. Due to these features, pure visual-only estimate will have physical artifacts like penetration shown in red here, or floating in the air shown in blue here. As shown before, the resulting scene in simulation will blow up immediately. We also tried other state-of-the-art single-view reconstruction methods. Unfortunately, they all suffer from poor segmentation, missing correspondence, or most importantly, penetration and floating. In contrast, our method is directly transferable to a Mujoko simulator. Our optimized shape has no penetration and makes support with the surroundings if it needs to form a stable pose. We only observe minor drift from the initial positions, and the simulated contact forces after settling closely matches our optimization result. under the example just shown, we test our method on 5 self-created cluster scenes, and they all result in stable simulation with negligible drift. We also tested the generality of our pipeline on clustered scenes from the YCBV dataset. Our method consistently generates simulation-ready scenes that are stable for long term. To sum up, we propose a real-to-scene pipeline that enables simulation-ready physics-aware reconstruction for cluster scenes we call Sparks. The secret sauce here is our proposed joint shape and pose optimization with multi-contact physical constraints. Please check out paper and webpage, and I look forward to chatting more during the poster session. Thank you.
Our next paper is Visor, Imperative Web-Based 3D Visualization for Python, presented by Bren Yi.
Okay, hi everyone. My name is Brent. I'm very excited to be here to talk about our project Visor, which is an imperative-style web-based 3D visualization library for Python. And this is done in collaboration with folks at Berkeley, CTU in Prague, as well as ETH Zurich. So the motivation of Visor is super simple, and that's visualization just makes life a lot easier for robotics. If we have things like joint angles or point clouds, these can be super cryptic if we just naively print the values, right? But if you take these same quantities, throw them into a 3D viewer, right, all of our systems just become much easier to understand, debug, and ultimately to build confidence in. So the key idea of Visor is that we want to make this problem basically easier and more extensible for researchers and developers. So Visor is a library that in Python that tries to make 3D visualization both easy and extensible. It has these two parts. The first is going to be a controllable 3D viewport, where you can throw in 3D assets. And the second is going to be a configurable 2D GUI, where you can build a 2D graphical interface. And for both of these, we basically provide a very simple Python API that lets you set them up and configure these things with just a few lines of Python. And so the key idea here is we can take these two components and compose them in lots of interesting ways. And what we found is that this basically lets us build these sort of bespoke tools that have really transformed the way we do everyday research. So if we want to build a 4D point cloud viewer, for example, or do any sort of interaction with things like meshes or IK solvers. And we've also been doing a lot of RL recently. So if you want to take an RL policy output, look at it in a web browser, this is something we can do. You also don't have to take my word for it. So we've actually been working on Visor now for almost 4 years. So there's a lot of in-the-wild examples of basically Visor used in different projects. Here's some work for human motion generation. We've also been connecting it to Majoko, so this is called MJ Lab. And there's also a lot of work in sort of the self-driving community of looking at self-driving data sets using Visor. Everything here is web-based, and why that's nice is because we can run Visor on things like a robot, connect over SSH, and then basically look at the visualizer from any web browser. So in this case, we're running some Python code on the robot, connect through the network, and then we can look at sort of the state estimation outputs with very, very little setup. Okay, and then finally, I'll just note that we live in kind of a magical time. So if you use something like Cloud Code, you don't actually have to learn how to use Visor. These days, you can just write a very simple prompt, like load the Frank paint.urdf using robot descriptions, have it write RSS 2026, show me in Visor, and then the LLMs will just figure out all the IK. It knows how to use Visor because it's been open source for several years, and it'll be able to build this kind of thing for you very quickly. With that, thanks so much for listening. If you're interested, we have all the code on GitHub. Everything's installable via pip. We also have our RSS paper, which has a lot more technical details on how we think about things like API design, software architecture, as well as benchmarks. And of course, I'll be at our poster, and I'd love to see you there if you have time. And here's a QR code that has a link to the website, as well as lots of examples and API reference. Yeah. Thank you so much.
Our next paper is Motion Uncertainty Aware, Next Best View Planning for Moving Object Reconstruction, presented by Karen Lee.
Hello, everybody. I'm Karen from Harvard University. Today, I'll introduce you a novel task of active view acquisition of an object while it moves. So you might be wondering, why don't we wait until it stops? Well, that's not the case for wildlife like sperm whales. To help biologists better understand sperm whale movements and social behaviors, we aim to deploy autonomous robots that can actively collect informative, diverse views. To abstract this as a first approach, in this work, we address a core planning problem of active reconstruction of a known rigid moving object. This problem, however, is not fully addressed by existing work. Next best view planners optimize surface coverage beautifully, but assume static objects. On the other hand, active tracking methods do not optimize surface coverage. And right at the intersection is where our work lands. Our key idea is to reformulate next best view planning as belief space viewpoint selection. So instead of selecting the best view for a single predicted object state belief, we select the best view that's the best under the entire future object state belief. And more concretely, we pick the viewpoint that maximizes the expected coverage, taking over a predictive belief of where the object is when the robot arrives. And more specifically, this belief is propagated twice into the downstream planning. And let me now unpack its 4 pieces. To score a viewpoint, we adopt a fast and efficient method from existing work, where we represent the scene using a voxel map. We cluster it into ellipsoids. Then, for each candidate viewpoint, the ellipsoids are then projected onto the image plane. This projection-based score rewards seeing a larger unseen surface and avoids re-observations. So where is the object now? To estimate the object's planar position and velocity, we use a Gaussian process smoother that fuses a constant velocity motion prior with the most recent noisy object positions. But what we really need is where the object is when the robot arrives. So using the current object state belief, we propagated a step forward to obtain a Gaussian predictive belief. And this belief is then used for candidate viewpoint generation and evaluation. We generate a set of viewpoints in an object-centric frame, meaning that the set travels with the object as it moves. The geometry reflects the predictive uncertainty, which dynamically adapts to the shape of the object position belief. Since not all viewpoints are feasible, we keep only the ones that the robot can reach within the planning horizon. To score a viewpoint, each realized object state induces a unique camera and object configuration, which gives a deterministic score. The expected score, however, admits no closed form due to nonlinearity. We therefore approximate it using a Monte Carlo estimate by averaging over the samples. And then we execute the highest scoring viewpoint, as that's what's driving the robot to continuously uncover new surfaces. We validate the full pipeline on hardware, where a sensing robot is actively reconstructing a moving object that follows a predefined path. We also stress test it across 3 different position noise levels. So to evaluate the performance, we measure voxel completeness. We compare our proposed framework against 2 baselines representing the 2 paradigms of work we bridge. The first one computes a score, but assumes the object is static, using the current estimate instead of the future. The second one accounts for the motion, but does not compute a score, serving as a lower bound. We can see that our proposed framework consistently outperforms the baseline across the different baselines, noise levels. Well, thank you all for listening, and I hope to talk to you more at the poster session.
The next paper is Relaxation-Aware Multimodal Sensing of Soft Gripper Driven by Structured Perception Learning by Qiji Shen.
Yeah. Hello, everyone. I'm the substitute speaker of this paper. Today, I will present our work on relaxation-aware multimodal sensing for soft grippers. Soft grippers are excellent for adaptive and safe contact. However, during long-term grasping, the interaction force gradually decays due to the viscoelastic relaxation in soft materials. Inspired by human grasping, which achieves stability through stiffness regulation, multimodal sensing, and continuous feedback, we aim to address these limitations. Stable long-duration grasping requires 4 key capabilities: compliant structure, tunable stiffness, continuous perception, and composition for time-dependent force decay. Existing systems only address subsets of these capabilities. To address this, we propose a variable stiffness software gripper with a relaxation-aware perception and control framework. The gripper integrates passive compliance, thermally tunable shape memory polymer beams, and switchable adhesion, enabling compliant, stiff, and adhesive grasping modes. Stiffness is controlled via temperature, allowing transmissions between gentle contact and load-bearing grasping. For perception, we use a non-invasive multimodal design. RGB and infrared cameras are placed as the gripper base instead of being embedded in the structure. RGB vision tracks the deformation, while infrared sensing captures temperature-dependent stiffness variations. To handle force decay, we model viscoelastic relaxation using a temperature-coupled reduced formulation. The model separates instantaneous elastic force from relaxation-induced decay. The instantaneous contact force network estimates contact force from poles and thermal features as contact on site. The relaxation composition network predicts the relaxation magnitude and time constant from current temperature and kinematics. We evaluate the system on a long-duration force-controlled grasp and hold task. Compared with a fixed aperture baseline and an instantaneous-only method, our approach maintains the target force more accurately, achieving a mean absolute error of 0.066 newtons. We test the real-time force perception under stiffness modulation using different objects. Results show that the stiffness affects the interaction behavior. Low stiffness improves sensitivity to weak contact, while high stiffness enables stable force transmission under larger loads. Despite these variations, our method maintains accurate force estimation across all stiffness conditions, demonstrating robustness to mechanical changes and contact diversity. In addition, we evaluate task-oriented stiffness selection in two scenarios: torque-demanding lead unscrewing and disturbance-prone cylindrical grasping. High stiffness supports torque transmission for successful unscrewing, while low stiffness improves conformal contact and disturbance tolerance for cylinder grasping. In conclusion, we present a mechanism AI co-design framework for stable long-duration soft grasping. Variable stiffness structure defines the feasible interaction regimes, while physics-informed learning compensates for viscoelastic uncertainty. Together, they enable stable and suitable substance force control. Thank you.
Our last paper of this session will be COCO in EKF, state estimation with learned contact covariance in dynamic contact-rich scenarios, presented by Michael Baumgartner.
All right, thank you. Good morning, everybody. With the recent rise in more dynamic motions, for example, dances, or also ground motions with very messy ground interactions, the need for a fast and reliable proprioceptive state estimation framework only increases. We propose a novel framework with the core change that we encode our contacts via contact velocity covariances instead of the more customary binary contact flags. And this has multiple advantages. First of all, these covariances are much more expressive, as they can encode even partial motion constraints, also in non-contact situations. Next, they are readily integrable in a standard INIKIEV framework in the process noise, and can thus be used to estimate the robot state directly. The only slight change that has to be made is that we don't switch the contact states on and off anymore, we keep them in the state at all times. With these two changes, our INIKIEV becomes readily differentiable since the covariances are naturally continuous. Thus, we can use it directly in the training loop via backpropagation through time to supervise our learned contact module on the end state. We evaluate our method against three state-of-the-art approaches. In the first non-learning-based approach by Hartley et al., they require force sensors or heuristics to retrieve the binary contact flags. In an extension work by Lin et al., our hybrid baseline, they utilize a learned contact module similar to ours to also retrieve binary contact flags. And then in an end-to-end approach by Yu et al., the state estimation transformer, they predict the state directly from the sensor input. We compare against different variants of these approaches. I refer to the paper for more details. We evaluate our approach in simulations as well as on real-world robot data, both for the dancing as well as the ground motion regime. And as can be seen here, we beat the other baselines across the board in terms of linear velocity estimation error, which was also the metric used during training. Here we visually compare the different methods. In green you can see the ground truth state of the dancing robot, and in beige the state estimate. And as can be seen for the classic INIKF that relies on heuristic contacts, it can diverge very quickly. You can't even see a state estimate anymore. In the top right you can see the end-to-end approach that really struggles with these extensive lateral motions. And for the other approaches that rely on binary contact flags, you can see a larger height drift than with our method. We also test the approach in the loop on real robot hardware for different real-world motions. And please note the inset render in the top left that shows the internal state estimate of our method and how it really aligns with the real robot state during the motions. These motions included unseen motions during training, like the previous moonwalk or this highly dynamic pirouette, and also a lot of seen motions that were used during training. For example, these ground motions with very ill-defined contact surfaces, and also dynamic barrel rolls. Now, importantly, since we depend on these more expressive contact covariances, we can support these motions with only a very sparse set of predefined contact points. And they can even be automatically sampled, as we show in the paper. Lastly, we also support a wide variety of other dancing motions that were directly used in the training loop to supervise our learned contact covariance estimator. If I've piqued your interest and you want to learn more about the approach and go more into detail about the derivations, please visit me later in the poster session at our poster. And I thank you all very much for your attention and wish you a great remainder of the day.
We'll now move on to the Q&A for the whole session. So we'll have all of the speakers come up, and we will start with the Q&A. So if you have any questions, please come. Yeah, you want to?
Hi. I have a question to Coco in EKF, Kalman filter. You showed dancing and motion on the ground floor, but did you test your method in the stairs, for example, or parkour with different height, like with variable height terrain?
Yes, very good question. So far we didn't. I also tested the approach for just normal walking motions, which works perfectly. I think what the question is getting at is if it's important that it's a flat terrain, for example. During training, we actually use a lot of domain randomization for the dances. So we use uneven terrain. We even use terrain where it dances downstairs or upstairs, but we didn't really have a physical setup. But it was part of the domain randomization, and there is nothing in the method that would prohibit it from working also with different heights.
Thank you.
Okay, we'll do one more question. Luca, do you want to go? And then I think we're really short on time because we had so many speakers.
So the question for the FreeOC paper, the first paper. So as far as I understand, the paper is first getting into a, where is the author? First paper? Okay. So as far as I understand, the approach is getting first to a semantic Gaussian plot and then converting that to a voxel-based map. Why not just directly doing raycasting and getting to the voxel-based map in the first place? Sorry if I missed it.
Thank you for your question. So in that task setting of supervised method, they always predict the 3D Gaussian splitting location and semantics. Then they do projection to occupancy prediction. So to form their evaluation metrics, so we also do the Gaussian splitting metrics to occupancy. That's the first reason. And the second reason is that we have tried to directly project the point cloud to occupancy, that whatever IOU or the MIOU of semantic metric will be lower. It also proved that Gaussian splitting can improve the surface information than point cloud directly to occupancy.
Just to clarify, do you guys compare against approaches doing semantic voxel-based map with raycasting? Because typically, like, when you get to a Gaussian splat to a voxel-based map, like, you actually lose a little bit of accuracy with respect to direct raycasting. We can chat to the poster, yeah. Okay,
yes, thank you very much.
Okay, well, let's thank our speakers one more time, and then we encourage people to come to the poster session.
Good. All right. Hi, everybody. Welcome to our final Early Career Spotlight for RSS 2026. It gives me great pleasure to introduce our speaker, Professor Wenzhen Yuan. Wenzhen is assistant professor at the University of Illinois at Urbana-Champaign, where she directs the RoboTouch Lab. If you work in tactile learning or tactile perception, you most certainly have seen or built upon Wenzhen's work. Her papers on high-resolution tactile sensors, such as the gel sight, has had tremendous impact in the field. In fact, you could see it actually across many of the papers and presentations at this year's RSS. Now, Wenzhen's work actually extends beyond the gel sight to the entire pipeline, from sensor design to modeling and simulation to perception and manipulation. And now she's also playing with dexterous manipulation, whole body tactile sensing, social and physical HRI, and soft robotics. She's a recipient of the IEEE RAS Early Career Award and the NSF Career Award, and now the RSS Early Career Spotlight. I personally am very much looking forward to her talk. Please join me in welcoming Wenzhen.
Thank you. Thanks very much for the very nice introduction, Harold. It's really an honor to be here. And there are so much fun things happening in the field of tactile sensing, and I try to build today's talk based on our recent efforts reviewing the field of tactile-based manipulation and in combination with my own journeys along this way. So I entered the field of robotics and started working on robotics tactile sensing since 14 years ago. And for those years, I'm trying to address this question: how we can make robots understand the touch and understand how to use touch to interact with the world. And definitely the first step is that we need to have a good sensor. So with that motivation, together with my
trying to fix it.
It seems good on stage.
No, they didn't switch to the right screen here. Okay, good. So with that motivation, together with my PhD advisor, Ted Adelson, and other lab mates, we introduced the optical-based tactile sensor gel sight into the community. So it uses optical design to get high-resolution geometry details about contact objects, as well as estimating the contact force based on tracking those motion of markers. So the sensor itself is fundamentally different from like a traditional array-based sensor, since that it's providing so much details about the contact geometry. So that opens lots of possibilities for perception and, of course, manipulation. But of course, like, although we know that like, there's lots of information here, it can tell robots more stuff, but like, how can robots effectively use them? It remains an open question, and also a question I've been asking myself and exploring for the past 14 years. And also, I believe the sensor is a starting point, it's not the answer, and it's an inspiration to tell us how does touch work and what's the fundamental mechanics of touch sensing for robots. So to try to answer these questions, again, like we're trying to look at beyond robots, looking to human again. And this is a homework for one of my PhD students, Jingyi Xiang. So ask her to observe herself in her daily life for doing all kinds of different things with her hand, with touch, and try to observe like why touch is important for humans. And a quick answer is that for those manipulation tasks that requires much precision, adaptiveness, and dynamic response, the sense of touch is very important. So of course, the next step, we want to move this to robots. How does it work for robots? It's not only a what question, it's also a how question. So this is definitely not a new question. So the community has been exploring this for decades. And also there's like a significant shift of the paradigms of how people address this question that moves from mechanics-driven methods to data-driven methods. But it's very interesting to look at like for years how people view this question and how people understand touch and how people leverage new methods for using touch. So starting from this kind of classical perspective or mechanics-driven perspectives, so it's how people have been doing this for years. It's like a very standard robot frameworks, like we come from perception and then goes to actions. So everything is defined by human here. Human decides like what is important for perception, how to do perception, and how does the perception result help manipulation, or in other words, help robots to better perform in the physical world or interact with the physical objects. So more particularly, this process can be seen from this flow. It's like we have the input of a sensor raw readings, which might be of very high dimensionalities, but through this perception modulus, which either be built through like analytical methods, model-based methods, or even machine learning methods, so we want to generate a descriptors of tactile sensing, which is typically of much lower dimensionality. And this descriptor becomes the input of the action modulus, which tells the robot what to do, and then it comes to an executable command for the robots. So the difference comes within like how people design those modulus, both perception modulus and action modulus. And the interesting thing is that like although there have been like hundreds of papers working on those things, but if you look closely into like how they view the perception problems or action problems for tactile-based manipulation, they can be categorized into some like very basic things like contact force and torque, contact localization, pose estimation, slip detection, and physical property estimation. So although it's like very high level, very abstract, which is very simple, but combined with like specific things and tasks, they can infer very rich information, and they can mean very different things for like specific applications. And on the action side, so correspondingly, so there are different ways for designing this modulus, such as like tactile-driven closed-loop control, or state transfer based on tactile feedback, or just use the tactile description method descriptor to update the low-level control based on the properties. So sometimes, like even for those very simple things, such as like the contact force and torque, localization, pose estimations, the robot can do a lot of things, and in fact, that covers a very, very big portion of the tactile-driven manipulation tasks happened in the past. So I would like to use the example of this, like one of my favorite old work developed in Belfield University more than 10 years ago. So these researchers designed this like tactile servoing frameworks using a relatively lower resolution tactile sensor. And they designed their descriptor purely based on the force and pose, and in combination with a PID controller and inverse kinematics, they asked their robots to maintain this contact descriptor, which is like based on force and pose, so that like it can follow. It can actually, it turns out to do many different things, such as like maintain over stable contacts or following the objects when there's some disturbance from the human. And this can even be done for this can even help for some more complicated manipulation tasks. For example, here they make their two dexterous arms holding an object, moving it around different axes. And the basic control framework they do here is also based on this tactile observability framework. They define what is a stable touch based on force and contact pulse. And they just plug in their PID controllers to maintain the stable grasp. And you can see that the robots can be very dexterous regarding moving the objects. Of course, things can be goes to more complicated end if we are considering high-resolution tactile sensors such as gel site. So this is one work my group has done about doing cable routing, and we want the robots to grasp the cables and going through different pillars and channels, and finally insert the cables into the slot. In this process, the gel site sensor on the fingertips is very essential to help robots to detect what is the contact is like. Even though this contact is indirect, it happens on the cable, it's not directly happened on the fingertips. But by measuring the fingertip force and the pulse or orientation of the cables, the robots can have a good understanding of is the cable interacting with the environment correctly? Have I successfully got the cable around the corners, or have I successfully got the cable into the slot? And this helped the robots to manage this very challenging task of handling this deformable cable. And sometimes this can happen in a very simple way. So this is another task where we want to make our mobile robots to move around the entire University of Illinois campus and try to open any door it saw on the campus. And the basic framework is based on vision, the robots try to recognize where are those door handles, door knobs, and based on the visual primitives in trying to understand how to handle those doorknobs and handles. But the tactile feedback here is especially helpful for robots to understand, are you handling the door in the correct way or not? When you rotating the handles, are you rotating in the clockwise orientation or counterclockwise orientation? Should you push or pull? Is the door locked or not? And actually, we didn't really use very high-resolution sensing. We just used a very simple sensing based on the current feedback of the robot arms. We can get a very coarse estimation about the overall impedance force on the robot gripper side. And this is already enough to tell the robots, are you interacting with the door in the right way? And you can see that with the help of haptics feedbacks, the robot is successfully opening different kind of doors around the campus. Okay, so that is a quick view about what are the simple things, contact force, orientations, and pulse estimation can help. And the next is slip detection. So this comes to the most common robotic task, grasping. We always want robots to hold some objects when we need to interact with the objects or interact with the environment indirectly through the objects. In all those cases, we want to make sure that robots can successfully grasp the objects and hold the objects in the hand, which is not always the case. When the robots didn't use enough normal force to hold objects, of course, the object may slide away from the robots. And this is something we really need robots to perceive and prevent. And tactile sensing is essential in this process to tell the robots, hey, your grasp is not stable, the object is slipping away, and you need to do something. But how does this happen? So there are different ways, but we found that with the help of gel site, we can very precisely see the location of the objects in the grippers by tracking the geometry, especially after we grasp the objects, lift it, and we track the geometry again after a very, very short time. And sometimes when we find that the geometry has moved, what does this mean? So this means that there have been some relative displacement, although very small, but this happens between the objects and the surface of the gripper. And that exactly matches the definition of slip, and that tells the robot something bad is happening, you should do something. But you may say that, what if the object itself is flat? It doesn't have any texture to help robots to track. So we found that in this case, we can still see the field of the markers on the sensor surface and track how they move as the time goes. So very interestingly, that you can see those patterns at the beginnings, all the markers move very homogeneously. But at some points, there's a big difference between the markers moving in the center of context and the peripheral area. And we found that heuristically it matched to the pattern of slip occurring. But actually, if you look into the soft mechanics about what's happening on this contact surface, this is because this slip didn't happen immediately, but it happens like from the gradually from the peripheral area to the central area. But on the sensing perspective, that means these mechanical views can help the robots to understand what is happening and a queue of slip is going to occur. And with the help of this, so we put this into a closed-loop control manners for robot grasping, where we ask the robot to grasp the objects with small force, but when slip is detected, the robots will increase the force, and until it's like use the force that is better enough to lift the objects without slipping. But in some other cases, we found that the most commonly seen failure of a grasp doesn't come from like the normal force is not large enough, but it mostly comes from the torque. Like if you're not grasping somewhere so like very close to the centroid of objects, there's a significant torque, even though the objects might be very light. And this is something you want to prevent. And instead of like changing the grasping force, the best strategy is to change the location of the grasp to make it closer to the centroid of the objects. And here again, like we use the tactile feedback to feel the torque, and based on the measurement of the torque and orientation of the torque, we tell the robots to navigate along the major principal axis of the objects until it gets close to the centroid, where there's a very minimum contact torque. Okay, so that summarizes the slip detection part. The next part is physical property estimation, which is like mostly considered as a perception problem. Like for example, like we have been looking into like estimating the hardness of objects, or like some properties of like fabrics of different fabrics. But sometimes the physical properties will also be important for the robots to understand how to better interact with the objects. So here I'm taking an example of liquid. So liquid perception for humans, like intuitively, you probably want to shake a bottle and feel the vibrations and understand like what's the properties of the liquids in the bottles. And we try to do the same things with a robot. So we ask the robots to do a very, very simple shaking, just like by impulse pushing of the liquids. And that actually generates lots of vibrations and can be like effectively captured by gel side sensors. And here, we reduce the dimensionality of these temporal signals to finally just a 1D sequence. And it actually match a 2D damping system very well. And we just use the descriptors of a damping system, which includes like the decay rate of the signals and the frequencies. And that well describes the properties of the objects. So for example, if you look at the comparison between different objects like water, oil, detergent, which are very different regarding to their density as well as viscosity. And we found that this vibration patterns differs a lot. And we can just use those two parameters to easily recognize what kind of liquid it is, but also actually we can do even quantitative measurement and get some estimation of what exactly the viscosity of the liquid is. And why does this matter? So we look into like one of very challenging tasks. We ask the robots to draw something with those with sauce in a dispense bottles. And this is challenging because those sauce, they are fluid, but they are very sticky. And if you look into like an academic word describing it, they are non-Newtonian fluid. So which means like their flow is also like time dependent and velocity dependent. So that is very, very difficult to perceive and very difficult to manipulate. But here we developed this like pipeline of perception first and then manipulation, where in the perception, we try to get some descriptions of this fluid, of this source properties that can be used to update the robot's strategies of squeezing the bottles. And here you can see that the robots actually firstly saw those two liquids. It's not in its training set. It's the first time, but the robots can do the perception and then decide to use different strategy, like moving the yellow cells much slower, but when operating this red cells, it's much faster. But finally, it can draw these patterns with like two sources, but with very consistent stroke. So this is not a very easy task. So here is a comparison of our methods of this perception manipulation pipeline in comparison with other more straightforward pipelines you can think of, such as using the weight as a feedback or preset of the volume as a feedback. But since the source itself is like a non-Newtonian fluid, so you can see that the final stroke it generates here is either it's not either. It's both not very even and didn't match the desired width of the stroke we want to achieve. So that like if we really want to make a very precise dispensing and make a very consistent stroke of this source, so this perception pipeline and understanding the physical properties is essential. Okay, so that summarizes our observations of how people manage to do use mechanics-driven methods to solve tactile-based manipulation problems. So it's highly based on the human understanding of context. So everything here is handcrafted. Human decide like what is important things for perception and how the perception result is relevant to like generating robot action. So my description of this method is that they're sensor invariant, although sensor dependent. So what does this mean? This means like if you look at individual papers, they're built upon like different sensors. It's like all the method developed is only applied to that particular sensors used by the research groups. But like the fundamental things behind it, like the fundamental drive here is that they understand the perception results from tactile signal and what is described these tactile signals. They are sensor invariant. And of course, like since like there's lots of human intuition here, so you know that well that when it will fail and when it wouldn't. But also it means like there's lots of constraints with limited contact conditions, so that it can hardly scale. So this is a question my General Z students ask me because they think like all those lines of research are really outdated. It's like we don't need to study them anymore. But I still personally believe that have a review of those like classical way of how people think about tactile sensing, how people use them, can give us a better understanding of the mechanics of our context. And even in this new eras of like manipulation, where like learning is pretty dominant, so this understanding of content mechanics can help us to better design this learning system. So going to the data-driven eras, you can see that there's lots of like nice works pop up in the recent years. Like lots of people trying to train different manipulation policies with tactile input, such as using reinforcement learning methods or imitation learning methods. And in recent years, there are also a big trends of like merging tactile sensing with VLA models. And this is typically happens by like augmenting the existing vision language foundation models with actual tactile input instead of like using tactile sensing as a part of a foundation model as well. Why? Because data. Because there's not a similar scale of large tactile data set ready to use to build these foundation models. So that like the way to use tactile sensing for VLA models is usually use them as augmented methods for like a vision-based method. So if we take an overall look at those data-driven methods, they show lots of promise, and they solve lots of problems where traditional methods can hardly solve, where they reduce the bias of humans in the system designs and can better adapt to like more noisy settings. But the biggest challenge here is that data. Especially this data problem is a big challenge for tactile sensing because if you work with the real tactile sensors, you know that tactile data come from the tactile sensors, but those real tactile sensors have their tempers and personalities, so they can hardly scale. So how to solve this? So I won't say that like there's a good enough answer here, but the community has definitely been working towards getting it better with this data challenge. The first method, definitely people have been looking into is simulation. So this is a simulator our group built like back in 2022, so where we use like a combination of physical insights and light data-driven methods to simulate jaw size sensors. And it can generate readings very similar to the real sensors. And here is an implication of application of our the simulators, where we ask the robot to grasp different objects in simulations, train a network for predicting the grasp results, and did a zero-shot transfer to the real grasping system. And because our simulated data is very, very similar to the real sensors, so this zero-shot transfer actually works very well and can achieve a success rate around 90%. So, but you can ask, like, this is already happens like 4 years ago. Why people still complain about sim-to-real gap? So here is my own understanding. I think for the sensor simulation itself, especially for gel-size sensors, they're good enough. They're almost ready to use. Of course, you can see that like if we're looking into a larger, bigger views about like different variants of gel-size sensors or like other kind of sensors, there's still way to go, but I think they're totally solvable. But another challenge pop up nowadays for more contact-rich tasks is the imprecision of the mechanical models for simulations and the gap between the coarse mesh and mechanical simulations and the fine mesh requirement for sensor simulations. So these are now problems in many contact-rich tasks where tactile sensing are not involved. But for the task that requires lots of precision, lots of fineness, like a very refined mechanical models is very important for like, this level of task. So another big challenge for the entire field of using tactile sensing is a domain gap. So here, I'm taking an example of gel-size sensors, which is what we are most familiar with. And you can see that for single objects here, it's screws. If we're using different sensors, or even like the same sensors but different manufactured patch or different variants of them, the image or the tactile readings we get, if we look at them like pixel by pixel, they are very, very much different. Although as a human eyes, you can all got the feeling that, hey, they are like some kind of like a screw with lots of threads on in the end. But if you make the robots to handle this kind of data, it's a big challenge. So that means like your models trained with data from one sensor can hardly apply to the other sensors. And this question is more complicated if you are considering like a wider range of sensors, like different kind of tactile sensors and different form factors and different sensing modalities, visual resolution, different noise models, etc. They will get very different readings when there's like when generating a similar type of context. So how to solve this? So we won't say that we have the best solution here, but we did some explorations in the categories of like in the category for gel-size-based sensors. So our idea is that like instead of using the raw readings of the sensors as an input of the system to train any models, so we probably want to design an encoder which generate like representation vectors that can be better used for different kind of downstream tasks instead of the raw reading. And of course, like sensor, we want this representation to be sensor invariant. So that means like our input can not only be the raw signal of this particular sensor, but also be some sensor-specific info, or sometimes we call it like sensor calibration data. So there's nothing special here. So very standard ways of making the encoder. But the challenge here is like how to train this network, how to gather data. So since our core goal here is to get this representation that is sensor invariant, so that means like we train the network must have with data from many different sensors, which is not very practical with the real sensors, because like you can buy a few sensors in your lab, but like how do you scale that up to like 100 sensors, 1,000 sensors? And we believe simulation is the solution here. So here, instead of using data-driven simulation methods, we believe like we need to turn to physics-driven simulation methods. So here, that means like the sensor is simulated based on first principles, and we can like model each optical parts in gel-size sensors. And once we can do the modeling, that means like we can randomize the parameters here. So that is exactly what we did. So based on the real designs of gel-size sensors, we try to randomize those key parameters, and it automatically generated 100 variants of the gel-size sensors, which are like have the results looks very similar on the same contact geometry, but again, like pixel-wise, very different. And we press those like 100 virtual sensors against like different geometries. And in fact, we collect like 10K different contact geometries. All of them are like well controlled. We have like perfect ground truth of what they are like. And in total, that gave us a data set of 1 million tactile images with a variance and well control of like different tactile sensors and different contact geometries. And we use this data set to train our neural network. This is supervised in 2 ways. One supervision is a contrastive learning, so as to de-weight the sensor-specific domain informations. And the other supervision is like on the geometry generation part, where we force this representation we generated to maintain the most important geometry information of the context. And this method actually turns very well for different downstream tasks. And it can do a zero-shot manner transfer to different kind of tactile sensors. So here is one downstream task we did is for like geometry measurement, or like for specifically is 3D shape reconstruction. So instead of the traditional ways of like reconstructing the shapes, we try to feed the raw readings of the sensors through this encoder, generate these representations, and using this representation to generate the surface normal and reconstruct the shape. And so here you can see that it works well for like both simulated sensors and real sensors. And in another task where we try to ask our sensors to contact the objects and recognize what kind of object it is, and localize where is the context. And again, we try to do this in a zero-shot manners, which means like the training data set is collected with one sensors, but like we test it on the data set collected with other sensors. And you can see that it works well for different sensors. Okay, so beyond those 2 major challenges of tactile data, there are more open questions. So in practice, when we try to work with tactile sensors on robots, we found that like the challenge doesn't come from the sensor itself, but sometimes it comes from the robots. And that means like beyond like the better sensing methods, beyond like better strategy policies for doing manipulation, the shape of the robots also matters. So here is a dexterous hand. Let's just look at very small things. This fingertip, which is like people trying to make them like a hemispherical shape, imagining that they can make good contacts of objects from all orientations. But that doesn't mean that it's the best shape. In fact, we try to ask our robot's hand to do different kind of fine-grained manipulation tasks, such as picking up small things, or like rotating the screws, or picking up the stacked bolts. And the shape I highlight here are the shape of the fingertips we have been using. And you can see that, like, according to the different shape of the fingertips, the performance varies a lot. And how to understand this? So we try to put this into automatic co-design framework where we parameterize the shape of this fingertip with 6 parameters, and we randomize for parameters and try to understand like which combination of the parameters generate the best manipulation results. So actually, after a lot of optimizations, those weird shapes turns out to be the best shapes of the fingertips for those particular tasks. And we believe like this shape matters, but of course we also want to have sensings. So here we try to combine the target shape of the fingertip with the target sensor design. So here we use the methods of like OptiSense Studio developed by our labs, which focus, the idea is also is similar. It's like using a physical-based driven methods to model the sensors and try to optimize the design parameters in the simulation until we get the best design of the jaw size sensor, which automatically generate the design which in the form of like where shall we put the camera, where shall we put the light, and what kind of material to use, what kind of geometry to use of the sensors. And we found that in combinations, we can get a good shape of the sensor, fingertips of the hands that can do manipulation nicely, but also with nice gel size sensors for this particular shape of the fingertips, which can get like lots of rich information about what the object is contacting and where is the contact. Okay, so with that, I'm going to summarize my talk. At the end, I would like to highlight my students who have been contributing excellently to all those works I introduced today. And thank you for listening.
Thank you, Wenzhen, for the wonderful talk. We have time maybe for one quick question. There are mics along the aisles. Okay.
It looked like that your hand design exploration ended up with something that resembles like a claw. And I was just wondering, like, have you tried something that's like more akin to human hands, where there's like a soft spherical thing and then there's nails, which you could use for like different tasks?
That's a great question. So we believe intuitively, we believe fingernail is very important for the hand. And I think this is design question or answering what is the best shape of the hand, what is the best sensor of the hand. It's a very large question. It's not something we can give the right answer immediately, but we are making our first step exploration. It's where we are. And in the future, I believe what you propose here, fingernails and considering the deformability of the contact surface, they are also very important design factors.
Thank you very much.
Okay. Unfortunately, we're out of time. Please join me in thanking Wenzhen once again. Okay, see you back here.
you see through my eyes? Why you come and go like tide? Never mind, no matter what suffice. Dead of night, when you can't let this happen again. You might be alone when I'm leaving. For now I'm crawling back into your bed.
Hold me, don't hold me down. Carry me, but keep my feet on the ground. That storm is coming down hard. I'm your shelter every time it storms. But if you leave me, I've been moving on. You'll have a hard time drying when the fire is gone. I'll hold you, I won't hold you down. Yeah, yeah, I'll carry you, keep your feet on the ground. You're strong, and I'm the merry darling.
choices, but to let go of you would be my day. How is your family? How are your friends? Every little tear that I trickle, oh, I see it all come to an end. Yeah, we're cruising, packing up our bags, we're moving, listening to our favorite song, to you all night long. And it's nighttime, catch another break and unwind. I'll be there with you, real soon. How is your night going? How is your world shining? Does it win? Does it howl? Does it blow just for you? I won't refuse nothing, and I won't abuse nothing. Will I ever get the chance to know the real you? I'm cruising, packing up our bags, we're moving, listening to our favorite song, to you all night long. And it's nighttime, catch another break and unwind. I'll be there with you, real soon. And I won't stop falling, I won't stop falling, I won't stop falling in love. And you got me started, you got me started, you got me falling in love. And I won't stop falling, I won't stop falling, I won't stop falling in love. And you got me started, you got me started, you got me falling in love. Yeah, I'm cruising, packing up our bags, we're moving, listening to our favorite song, to you all night long. And it's nighttime, catch another break and unwind. I'll be there with you, yeah, we're cruising, we're cruising, we're cruising, we're cruising, yeah, we're cruising, packing up our bags, we're moving, listen to our favorite song, to you all night long. And it's nighttime, catch another break and unwind. I'll be there with you, yeah, we're cruising, packing up our bags, we're moving, listening to our favorite song, to you all night long. And it's nighttime, catch another break and unwind. I'll be there with you, real soon.
I wanna love you, I want to love and treat you right. I wanna love you every day and every night. We'll be together under the roof over our heads. We'll share the shelter on a single bed. Is this love? Is this love? Is this love? Is this love that I'm feeling? wanna know, wanna know, wanna know. I'm willing and able. So I lay my cards on your table. I wanna love you. I wanna love and treat you, love and treat you right. I wanna love you every day and every night. We'll be together with the roof over our heads. We'll share the shelter of my single bed. We'll share the same room. 'Cause Jah provides the rent. This love is this love is this love is this love that I'm feeling. Is this love is this love is this love is this love that I'm feeling. Is this love, love, love that I'm feeling? Tell me the love, love, love that I'm feeling. Tell me if you love now. Oh, I wonder now. Tell me if it's
yeah. So has this been a long travel for you?
Yes.
Yeah.
I'm not allowed to complain.
Exactly.
No complaining.
No comment. I am jet-lagged, but it's fine. No complaining.
That's all right. But we just had the same experience with Ikra, right?
Yes,
So it's the
yes.
other way around.
For you, it was easier to travel this time.
Sorry, what?
This time the travel was easier.
Oh, yeah, definitely. 3.5 hours by ground back. I can drive or I can. For once. Okay. Okay. Should we start? Okay, good morning, everyone. So we are now back to sessions, and we are at our 19th session, which is a planning session. My name is Hannah Kunyawati. I'm from the Australian National University, and next to me is
Stefan Leutenecker from ETH Zurich.
And we will start with our first presenter, Xuangjin Jin. The title of the paper, FACT-UMDP.
Hi everyone, I'm Shenjing from Shanghai Jiao University. I'm here to present VACUMDP, a vectorized PondDB planner for real-time autonomous driving. A dense urban driving scene raises a plethora of uncertainties. Perception is imperfect and actions are noisy. Agents may have unknown intentions and driving styles. To play on the uncertainty, PondDP's, in particular belief tree search algorithm, has offered a principled approach. However, as the number of interacting agents grows, the possible combinations of hidden factors leads to an explosion of uncertainty. So the problem is how to perform large-scale PondDB planning in real time. Our answer is massive parallelization. However, PondDB planners are hard to parallelize. Hybrid CPU-GPU methods such as heap despot requires frequent communication between CPU and GPUs, while GPU-native methods avoid such communication but suffer from branch divergence when different scenarios lead to different simulation results. So our methods take a new approach, CPU-native SIMD parallelization. When given a single instruction, SIMD operates the same operations across different elements of the vector, achieving CPU-native parallelization. Also, SIMD can be further combined with multithreading for enhanced parallelization. The key to enable SIMD is vectorization, vectorizing all computations. Back to the PondDB planning pipeline, we have 3 components. First, we sample a set of hypothetical scenarios from the belief. Then we perform trajectory PondDB planning, and finally, we perform trajectory optimization. The key problem is how to vectorize PondDB planning. The first step is that we need to refract planner into a data-oriented design. For any array of structures, we need to transform it into a structure of arrays. For example, when sampling scenarios, instead of storing the fields of scenario into a structure, we gather the same field from different scenarios and organize them into arrays. Doing so, we can use structures of arrays to store a batch of scenarios. The second step is to vectorize tree structures. For both belief and spatial trees, we flatten them, so that we can easily gather data from them to form SIMD vectors. Based on that, we have 3 levels of parallelization. First, global vectorization batches the simulation of transition dynamics across nodes from different scenario trees. Then, local vectorization batches collision tests within one node, leveraging vectorized spatial tree traversal. And finally, multithreading is also combined to parallelize different batches of scenarios. Together, these algorithmic designs enable our planner to simulate more than 10,000 futures within 40 milliseconds. Compared to the serial planner, it achieves hundreds to thousands times of speed up. With this level of efficiency, it achieves the state-of-the-art performance in the new plan benchmark. It drives efficiently and safely in dense urban scenes. Note that it achieves this with only a 40 milliseconds of planning time and requires no training. Here are the key takeaways. Search algorithm can be combined with data-oriented design to enhance CPU-native parallelization. And one can combine global vectorization, local vectorization, and multi-threading to maximize the usage of CPU. When done correctly, these techniques can deliver massive speed up and superior performance. Thanks for your attention, and please check the website for code and more results.
So the next paper will be presented by Sang Su.
Good morning, everyone. I'm Shen Xu, and today I will present our work from reaction to anticipation, failure recovery through agentic task graph for robotic manipulation. The main question we study is how can robots recover from failures efficiently in long horizon manipulation tasks? So robotic manipulation in the real world is fragile. During execution, objects may slip, cups may tip, and humans may disturb the scene. Existing methods usually react after the failures happen. One option is backtracking and re-executing, but this wastes already completed motion and may repeat risky transitions. Another option is VLM replanning, but calling large models online introduces high latency and cost. So reactive recovery is often too late for real-time and long horizon manipulation. Our key insight is very simple. We prepare recovery plans in advance rather than fixing problems after failure occurs. The system prebuilds backup branches for common failures. Once an error is detected, the robot can directly activate these present actions without replanning. Now I will briefly introduce our framework. The agent control takes task commands, sensor observations, robot states, and skill libraries as inputs. The first agent is a task agent. Given the instructions, it builds a nominal task graph, where nodes represent semantic subgoals and edges represent constraint-aware transitions. The second agent is a recovery agent. For each edge in the task graph, it predicts likely failure modes and augments the graph with forward-moving recovery branches. And the third agent is the execution agent. It combines both nominal and recovery branches into execution programs together with online monitors. So this enables low latency switching during execution. The whole system can be understood as a choreography of three agents. The composer structures the task, the arranger prepares recovery, and the conductor coordinates execution. This gives us an interpretable and modular framework. Yeah, we evaluate agent control extensively in both simulation and real-world scenarios with external disturbances, compared with previous approaches including DOREMI, recap, and code as monitor. Our method achieves better task success while keeping much lower reaction delay. These experiments clearly verify the superiority of our proactive recovery strategy. Here, we show more qualitative results across different tasks, including simulation and many real-world manipulation tasks. Our robot successfully handles various unexpected disruptions in all these scenarios. These examples show the diversity of tasks and disturbances, demonstrating our method's strong generalization across daily robotic operations. Yeah, beyond online recovery, agent control can also generate useful recovery trajectories. We use these failure recovery trajectories to fine-tune a sim-to-real policy. The results show that the recovery data can improve policy robustness under failure scenarios. To conclude, agent control reframes failure recovery as proactive preparation. It anticipates recoverable failures before execution and switches to prepared branches without replanning. The key advantages are proactive recovery, immediate switching, and modular design. Thank you for your listening. I'm happy to take any questions in the post-session.
And the next paper is going to be presented by Hangxin Xiao.
Hi, everyone. My name is Anxin. I'm excited to present hypothesis-driven uncertainty-aware model expansion for open-world robot planning. Given ability to predict and evaluate the effects of its action, the robot can use planning to act rationally for long horizon and constrained tasks. However, deploying such rational robots in new homes for open-world tasks such as preparing a meal remains challenging. Objects may be unobserved. Attributes are known, like zero sugar. And the action effects are clear. For example, time increased after pressing a button. With such an incomplete word model, how can a robot effectively plan? Intuitive ideas to use language model common sense to fill gaps in the word model. However, such expansion relies on common sense estimates that may not hold in robot-specific environment. This motivates our core idea. Robots need to expand the model continuously on the fly, and they should also plan ahead under uncertainty of such model expansion. In this work, we explore methods that try to extract the model expansion hypothesis from language model and plans while considering their correctness. We represent the robot knowledge as a current maintained scene graph and the potato domain, and the model expansion hypothesis is represented as a set of hypotheses. And the language model generates the initial set of hypotheses based on current available information. During planning, each hypothesis is represented as a variable with binary belief. And the verification actions are automatically generated, and we apply all-account determinization for planning. During execution, the VLM will perform verification actions based on observations, and the incorrect hypotheses are regenerated. We evaluate 6 methods based on 2 planning backends, the formal planner and the language model planner, and we consider 3 cases: without model expansion, with model expansion, and with uncertainty-aware model expansion. And we evaluate in 2 domains: block processing world, where processor produce unknown effects, and open world mobile manipulation in both simulation and the real world. The results in block processing world demonstrate that explicit model expansion is crucial for planning under incomplete word knowledge. And incorporating the uncertainty awareness further improves performance across all planners. These trends remain consistent in mobile manipulation domain. Here is a real-world task: deliver a zero-sugar drink to the table. The robot first hypothesizes that there's a zero-sugar drink in the fridge, and they open and verify there's indeed a drink inside. And the robot grasps the object using model-based planner, and visually verify this drink is not zero sugar. And the robot updates its hypothesis based on the new information and the generated plan. It navigates to the kitchen island and verifies there's another drink there. And it grasps the drink using whole body motion planning. And finally, it verifies, okay, this one is the zero sugar one, and take it to the table. All methods can generate 2 more diverse tasks, including heating up a chicken burger, finding a remote with a red button, figuring out how to switch off the living room light, and even operating an unfamiliar microwave. Thanks for listening. Please come to my poster section for more details.
And the next speaker will be Yuan.
Good morning, I'm Yuri from KU Leuven. Today I will present Elvis, ensemble calibrated long horizon latent imagination for visual MPC. Our work started from visually challenging industrial tasks such as shot treating and paint spraying, where dust and spray can severely occlude the camera. And they share similar overall structure as general purpose robots such as Pile 5 performing household tasks. To solve these tasks, we need, for one thing, memory to retain information over a long horizon, uncertainty awareness to handle unreliable real-world observations, and multimodal planning to preserve multiple valid strategies. Elvis places these 3 components inside one simple general-purpose world model reinforcement learning framework. Our goal is to provide practical realizations of these basic ideas and show that even in this simple form, it achieves state-of-the-art performance. Our framework is modular, so improving any individual component may further improve the full system. We adapted a standard recurrent state space model from the Dreamer series as a base for the long horizon world model. The key question here, though, is how long the imaginary rollout should be to remain trustworthy. To answer that, we train an ensemble of value functions and measure their disagreement along imagined trajectories. After normalization with running statistics, this disagreement indicates when predictions become unreliable. And we use this uncertainty to construct a time-varying lambda return. When uncertainty is low, Elvis trusts longer imagined rollouts. When it increases, it relies more on bootstrapped values. This provides a calibrated return for both actor-critic and online planning. We perform multimodal MPC for high-quality actions. Different mixture modes receive action sequences sampled with different ratios of random and policy prior trajectories. Prior heavy modes exploit learned policy, while random heavy modes explore alternatives. And each mode is then optimized independently, allowing the planner to preserve several coherent futures. To verify the proposed recipes, we first validate our method with 14 DMC visual control tasks. Our method achieves SOTA performance against 2 strong baselines. Our ablation shows that longer horizon and multi-modal planning are the key performance boosters, and uncertainty awareness serves as the main stabilizer. We further verified zero-shot transfer performance on a visually challenging sand spraying task. This task serves as a proxy to the shot reading and paint spraying task we saw in the first slide. Our results show that both memory and online planning are the deciding factors to a successful zero-shot transfer. In conclusion, Elvis combines long-horizon memory, uncertainty-aware imagination, and multimodal planning within a simple RL world model framework. Our next step is more compute-efficient planning together with improvements in each component. More details, videos, and code are available through the QR code. Thank you.
The next presenter is Kaufik Jakala.
Thank you for the introduction, Hannah. Good morning, everyone. Environment monitoring robots are often used to map correlated data fields, such as ocean salinity and temperature. Our objective is to find the shortest, most efficient sensing path that maximizes information gain. Early methods used mutual information as the objective function, which provides near optimal approximation guarantees. But the method is computationally expensive. To reduce compute costs, many planners leverage variance-based methods, such as optimal design metrics. These are fast to compute, but lack formal approximation guarantees. A third highly relevant class of planners focus on estimation uncertainty guarantees. These provide an upper bound on the predictive variance, which in turn lower bounds the true mean squared error. More importantly, they remove a major IPP bottleneck by replacing manual tuning with dynamic calculation of the number of required sensing locations. The problem is that current approaches are limited to stationary correlations and convex environments. Our approach is a comprehensive solution that provides near optimal approximation guarantees with low computational complexity. Crucially, it provides estimation uncertainty guarantees even in non-convex, non-stationary environments. We begin by initializing a Gaussian process fitted to prior data. We capture non-stationary correlations using attentive or physics-informed kernels. We leverage this theorem to upper bound the predictive variance. Essentially, it allows us to determine ahead of time if a specific environment location will drop below the target predictive variance if we choose to sense at the candidate location. Using the previous theorem and the learned kernel covariances, we compute a sensing field of view for each candidate location. These regions define exactly where a measurement is guaranteed to drop the predictive variance below our target. Using these sensing fields of view, we formulate a submodular objective function that tracks the number of newly covered environment locations. The algorithm then greedily selects the sensing locations to maximize this objective and routes them using a TSP solver. Since the objective is submodular, we are able to provide near optimal approximation guarantees. We benchmark our planner's greedy cover and the budget-constrained GCB cover using real-world topographic data. Our key insight is that our planners successfully satisfy the maximum posterior variance requirement while utilizing significantly less travel distance compared to representative baselines. Here's our solution alongside a baseline approach. By leveraging non-stationary correlations, greedy cover achieves 85% faster processing time, utilizes 80% fewer sensing locations, and reduces the total travel distance by 73%. In summary, our work provides a comprehensive approach to informative path planning with near optimal approximation guarantees, fast runtimes, and estimation uncertainty guarantees, even in non-convex, non-stationary environments. Finally, we validated the method through successful real-world field trials using an autonomous surface and underwater vehicle.
The next speaker is Danfei Su.
Hi everyone, my name is Danfei. I'm excited to introduce a new benchmark called Kinder. This is a joint work by Tom Silver's lab at Princeton and my lab at Georgia Tech. Unfortunately, all of the student authors could not be here, so I'm just presenting on their behalf. So why am I talking about a benchmark in a planning session? Well, this is because most of the robotics models today are still really bad at planning. In this example, excavator operator must reason about both the machine's kinematics and how its motion affects an environment. This is especially challenging because the operator controls the excavator only indirectly through a control interface. And in contrast, this dog fails to reason about a simple geometric constraints. And physical reasoning is hard, even when the failure looks obvious to us. Kinder focused on the 5 core challenges. The first is basic spatial reasoning. Here, the robot must understand what it means to place the drink behind a red bowl. The second challenge is non-prehensile manipulation. Here, the robot must use a sweeper to sweep several objects into a drawer without having to grasp each object individually. And the third challenge is to use. Instead of moving objects one at a time, the robot can use a box to move several objects together more efficiently. And the fourth challenge is to reason about implicit geometric constraints. For example, when packing object into a tight and cluttered space, the robot must avoid both object-object and object-robot interaction. As the number of objects increases, the number of constraints the robot must consider also increases exponentially. And the final challenge is dynamic interaction. To throw an object, balance a tray, dribble a ball, the robot must actively control a dynamic system efficiently. And with the challenge in mind, this paper introduces Kindergarten, a collection of 25 environments designed around these physical reasoning challenge. Each environment defines an infinite task distribution through procedural variation, and we also provide more than 1,000 human demonstrations across tens of these environments. And Kinder differs from existing benchmark in different ways. Benchmarks such as Liberal primarily evaluates task generalization. Behavior 1K focuses on household tasks, and the other benchmark provides broad environment coverage. But Kinder instead really isolates physical reasoning itself. The tasks have explicit kinematic, geometric, and dynamic challenges, and the system uses procedural variation to test both learning-based and model-based methods. And our second contribution is Kinder Gym, a Python package built around the gym-like API. It includes environments, more than 20 parameterized skills, and several interfaces to collecting demos through teleoperation interface like VR devices. It developed 13 baselines across 8 environments and released a reproducible implementation for all of the methods. The main result is that really all methods struggle with most of these tasks. And methods with more structure prior, such as task motion planning-based method, generally achieve higher success rate. And as a specific example, in the sweeping task, the robot must open a drawer, grasp the sweeper, and sweep all the objects into the drawer. The VLA 5.5 fails to grasp the sweeper. Diffusion policies attempt reach the sweeping stage, but fail to execute a non-prehensile manipulation. So different methods really fail at different stages of the task of the same physical reasoning problem. And we also conducted a real-to-sim-to-real experiments on a mobile manipulator, and these experiments really shows that the simulated challenges map to reality in meaningful ways. To conclude, Kinder provides a unified framework with 25 procedurally generated environments, a gym-like package, over 1,000 human demonstrations, and 13 baselines. And across our evaluations, none of the baselines consistently solve these tasks, which shows that physical reasoning remains a major gap despite the progress in robot learning. Thank you, and see you at the poster.
The next speaker is Kai Pfeiffer.
Thank you very much for this very nice introduction, Hannah. And I have the pleasure today to talk to you about this contribution entitled Integrated Hierarchical Decision-Making in Inverse Kinematic Planning and Control. So this research evolves around the L0 norm. So the L0 norm is not very widely used in robotics and is a rather conceptually simple concept here. So it counts the number of non-zeros in a vector. So here in this very example, we have a nonlinear function f in the dependence of the resource x, and we have 3 non-zeros. And despite its simplicity, this concept is very powerful and has been historically used for decision-making. So one example here would, for example, be in robotics, where F presents the forward kinematics of a manipulator. And now in each entry of this decision function here, we can see that we measure the Euclidean distance between the end effector and one of these cubes on this workstation. And now if we solve this optimization problem here, we minimize one of these distances between the manipulator and one of these cubes, and if we do this iteratively, this enables us with optimization-based methods to clear these workstations from these cubes. And how about constrained or hierarchical decision-making, which is the contribution of this work here? So here on the first level, we would like to identify inverse kinematic postures of this robot to select one of these 200 stepping stones, and then on the second level with the remaining resources, we would also like to place the hands on one of these 200 handrails. And we propose a nonlinear hierarchical framework here, which enables us to do exactly that. And here we can see the nonlinear solver iterations leading to these decision-making inverse kinematic postures. And what exactly is under the hood of this nonlinear programming framework? So we call this as SHNLP, and this is this rather bulky optimization problem, and this is hierarchical. So here we can see the index L, which represents the hierarchy levels from level 1 to P. And on each priority level now, we would like to minimize the slack variable with respect to the L0 norm. The slack variable relaxes our decision-making constraints F. So here from the constraint set or the decision set C, then also we have the set of inactive decisions which we have not made, for example, in terms of inequalities on the priority levels, previous priority levels 1 to L-1, and then also we have the active constraint set, which is the decisions which we have already done on the previous priority levels. So to summarize, make a decision on level 1, with the remaining resources make a decision on levels 2 to P-1, and then finally we make a decision on level P. However, the at-zero norm is discontinuous, so we approximate it with the smooth logarithm, and this prioritization shows us that this is advantages over weighted formulations due to the log scales. So this is rather impractical if you would like to weigh different decisions against each other. And now we can solve this with nonlinear programming, or SQP here in this example, and as a central contribution, we propose a sparse hierarchical QP solver, so much more efficient than standard QP solvers, and we enter a branch here, planning, and we adapt the trust region, measuring the quality of our substep, and also if the step threshold is below, so then we can also pursue to the next priority level. And then also we have a control branch where we have a constant trust region finely tuned. And in the future, we would like to extend this optimization-making robustness for decision-making to learning. So I would be very enlightened if you could help me here clarify some things towards combining optimization-based methods and learning-based methods. So I hope to see you at the poster session. Thank you very much.
Okay. Next, we have Miao Miao Dai talking about HOP.
Okay. Hello, everyone. I'm Miao Miao from IAP Lab in Shanghai Jiao Tong University. Today, I will talk about HOP, Fast Differential Dynamic Programming for Horizon Optimal Trajectory Planning. So the main question is simple. Instead of manually choosing how many time steps a robot should plan for, can we optimize that horizon accurately and efficiently? Traditional optimal control problem usually assumes a fixed horizon t, but in robotics, different tasks or environment may require different horizon t. So in this work, we also treat t as a decision variable, and we try to optimize the trade-off between the task performance and time. For a fixed horizon problem, recursive recursion gives us a structured solution. But when T is optimized, this structure is broken, and we can no longer use recursive anymore. So existing methods mainly have two directions. The first one is nonlinear programming method. It is general, but usually time-consuming. The second one is shift horizon approach. It is fast because it reuses value function of recursive, but it only works well for simple systems like linear or time invariant system. So our goal is to keep the efficiency of recursive while also find high quality solution for harder systems. To solve this problem with recursive, a naive solution is to try every horizon and make recursive recursion each time. That's absolutely correct, but it repeats a lot of computation. Our key insight is that instead of reusing the value function, we reuse the map between the value function. So we rewrite recursive in inverse form, and it becomes an LFT, linear fractional transformation. Since LFT is closed under composition, and it can be represented by three matrices, E, F, G. So we can just keep updating E, F, G recursively and use the intermediate result to construct our composed map to avoid repeated computation. Here is our algorithm workflow. So we use system information to calculate the LFT parameters, E, F, G. Then we compute the small g composed map. Finally, horizon selection becomes a fast query. We just apply the composed map, get the initial cost to go, and evaluate the cost for every horizon. And our HOP DDP use HOP LQR as the horizon selection module inside DDP. So the time complexity is reduced from O(n) squared to O(n). Here is our result. So we got up to 40 times faster than brute force method and significantly faster than NLP as well. We also have a higher success rate on harder problems. Finally, and most importantly, we got exactly the same optimal solution as the brute force method. Here is the demo of cut pole and quadrutor. As you can see, our method not only runs fast, but also find high-quality solutions. In the end, if you are using IOQR or DDP with a time penalty, try HOP. Thank you. Our code, website, and tutorial are available here. Thank you.
Okay, next we have Taiki Ishigaki talking about implicit null space manifold generation.
Thank you. Hello everyone, I'm Taiki Ishigaki from Tokyo University of Science. So today I present our work, implicit null space manifold generation for redundant robot systems. This is joint work with Sabira Karia from the University of Technology, Sydney. Redundant robot has many configurations that can achieve the same tasks. In this work, we use the task Jacobian to explore feasible configurations. We represent the sample solution as a Gaussian process implicit field. The field provides both a distance value and the direction toward feasible configurations. Here, we illustrate the problem using a redundant robot arm. Even when the end effector pose is fixed, the robot can take many different joint configurations. Inverse kinematics return one solution, while null space controller allows the robot to move between nearby solutions. However, the explored solutions are usually not retained as a reusable representation. Our objective is therefore to sample these feasible configurations and represent their structure in configuration space. So, and then we defined a task map, P called FQ. So where Q is the robot configuration and P presents the task. The task may describe a link position, a trajectory, or an object surface. Our method has two main steps. First, we use the task Jacobian. We move around local null space direction and maintain the tasks. This generates samples of feasible configurations. We then use these samples to construct a Gaussian process implicit field in configuration space. Once constructed, the field provides a distance value and its gradient. Here we visualize the null space manifold obtained by our method together with the distance field. On the left, we show a 3DOF planar arm with a two-dimensional tasks. In that time, Jacobian guided submaric generates a one-dimensional structure in configuration space. On the right, we show a 7DOF arm with a six-dimensional task. The field was constructed in around 9 milliseconds. In this video, we use the distance field to guide the robot toward the solution configuration shown by the red point. For each query configuration, the field provides a distance to feasible solution manifold and a gradient point toward it. Each query takes around 10 microseconds. A task does not necessarily have to define as a single target point. Finally, we conduct a preliminary investigation using a line and surface task. Here we show example where the end effector can lie anywhere on a given line or surface. The result suggests that continuity in task space can be represented as a continuous structure in configuration space. There are still several points to investigate further. So thank you for listening. Please come and visit our poster. I'm very happy to discuss with this work with you. Thank you.
Okay, next we have Wang Xi and Jingjuan Tang, who will be talking about how to exploit agile mobility of steerable wheeled mobile robots.
Hi everyone, I'm Xi Wang from Shanghai Jiao Tong University. Each wheel of a steerable-wheeled mobile robot can actively rotate around its axis, allowing the robot to move omnidirectionally. These robots have been widely adopted in industrial automation. However, there is still a lack of an effective and general motion planning framework. The main challenge comes from the limited steering speed of each wheel. This limitation must be considered during trajectory planning. Unfortunately, the steering constraint is tightly coupled with the desired robot motion, resulting in a highly nonlinear constraint. It also introduces singularities into the optimization problem. Since these challenges have not been fully addressed, most existing planners rely on heuristic strategies that are designed for specific scenarios, making them difficult to generalize. To address this problem, we first discretize the problem. By exploiting the half-cycle symmetry of wheels, we show that the feasible velocity set of a wheel can be represented as a cone. Each cone can then be expressed using a pair of bilinear inequality constraints. This leads to our original optimization problem, which we denoted as problem P. However, general-purpose solvers often suffer from numerical issues on P and are not fast enough for real-time planning. We then develop an optimization algorithm for this problem. At each iteration, we construct a convex optimization problem whose feasible region is contracted. After solving the convex problem, we use the solution to construct the next convex approximation. By repeating this procedure, the solution gradually approaches a stationary point of the original nonlinear program. The key component is how we construct this convex problem, which we called problem Q. We develop a convex concave decomposition of the bilinear constraints, as shown in the slides. The entire construction process is represented by operator S. We prove several important properties of this operator. These properties guarantees that the iterative process is well-defined and provide the theoretical foundation for convergence. Based on these results, we designed a complete optimization algorithm. We further prove that the objective value monotonically improves throughout the iterations, and that the algorithm converges to a stationary point of the problem P. Moreover, thanks to the properties of operator S, our intermediate solution proceeded during optimization remains feasible. This means our method is anytime feasible. Optimization can be terminated at any iteration while still producing a valid trajectory.
We evaluate our method on a challenging motion planning task with a planning horizon of 100 time steps. The objective is quadratic, while the nonlinear tracking error is linearized using a first-order approximation. We also impose a maximum wheel speed limit to better reflect practical robot constraints. Finally, we compare our approach with two general-purpose solvers and one solver specifically designed for SWMRs. The active set solver completely fails to solve this problem. The interior point solver returns trajectories that violate the steering constraints. Compared with the existing solvers, our method consistently achieves better optimization performance. Another important advantage is iterative refinement. Our algorithm can continuously improve the trajectory while maintaining feasibility throughout the optimization process. In contrast, the baseline SWMR solver violates the steering constraints from the second iteration onward. Therefore, our method not only achieves better planning quality, but also provides reliable anytime performance. Thank you very much for your attention.
Okay, next we'll hear about sampling-based follow-the-leader motion planning from Nicolas Baldassini.
Thank you. Hello. I'm Nicholas from the Continuum Robotics Lab at the University of Toronto, and I'll be talking about sampling-based motion planning for continuum robots. So if you're unfamiliar, continuum robots are known for their compliance and high degrees of freedom. They have applications ranging from minimally invasive surgery and industrial inspection. A key motion primitive in these applications is follow-the-leader motion planning. In our work, we assume that the robot is mounted to a 6 degree of freedom base, greatly increasing the amount of paths that we can follow. This 6-DOF base also increases the complexity of the problem, rendering traditional optimization approaches insufficient. Additionally, with our method, our method is model agnostic, meaning that any type of computer or any type of continuum robot can be used in this motion planning. To begin, given our path, we discretize it into a sequence of waypoints. Then we recognize two necessary properties for follow the leader motion. Property 1 is tip tracking, which ensures the tip of the robot touches each waypoint as it's being inserted into the path. And property 2 is shape following, which minimizes the deviation between the portion of the inserted robot and portion of the path. If your motion plan abides by these two properties, then it's follow the leader motion. So to shift a lot of the compute offline, we employ a concept known as shape libraries. With these shape libraries, we pretty much compute a lot of possible forward model configurations into a giant database. And because we're pre-computing this offline, you can use any type of forward model regardless of how complex or how slow it might be. And the idea is that in the online phase, we can effectively skip forward model computation by just sampling this shape library. So the idea is that as we're inserting the robot into the path, at every waypoint, we want to find a shape from the library that most closely matches the current subset of the path. We do this by aligning each candidate shape with the current path, which is what you're seeing right now. Once the shape is aligned with the path, we can calculate its deviation between the robot and the shape and the path, and then we just choose the shape from the library with the smallest deviation. So we could linearly search over the shape library, and if you do, we prove resolution completeness. But to make things a little bit more faster, we can actually group similar shapes together into clusters and then use a search algorithm similar to depth-first search to efficiently search through this shape library. So doing this process over each waypoint yields a sparse motion plan. So at every waypoint, we have a continuum robot configuration and a base pose pair for each waypoint. And now the problem is, how do we effectively interpolate between these waypoints while still abiding by those two follow the leader properties? We can do this by slurping between the tip poses and then linearly interpolating in joint space. And if you do that, naively, you kind of just get this interpolation that has a lot of shape deviation. So what we can also do is exploit the natural radial symmetry of continuum robots to conveniently adjust the base pose while maintaining the same shape during interpolation. In this work, we show that with that three-step shape alignment phase, we prove guaranteed tip tracking in the sparse motion plan, and we also show asymptotic perfect tip tracking during interpolation. We observe 4% shape deviation in simulated models, and the whole motion plan takes only a few seconds to compute with the cluster search version. We hope that this work expands the applications of continuum robots, and I'm happy to talk more at the poster session. Thanks so much.
Then next we have Wenzhen Li talking about certifiable gradient-based contact reach manipulation.
So hello, my name is Wenzhen, and today we study the computation of reachable sets on the contact dynamics and controller synthesis. Contact dynamics are inherently non-smooth due to the switching between active and inactive contact constraints, violating the smoothness assumptions typically associated with trajectory optimization. Moreover, before contact happens, actuator motions do not object the state. A common approach is to smooth the contact dynamics to obtain differentiability. However, smoothing introduces bias and does not preserve the constraint satisfaction guarantees. Our contributions are threefold. First, we derive error bounds between the non-smooth and smooth dynamics. We then implement a custom differentiable simulator to compute the required sensitivities and use these bounds to construct reachable tools for controller synthesis with guarantees for constraint satisfaction. We model contact dynamics by a second-order cone program whose optimality conditions enforce momentum balance, friction cone constraints, non-penetration, and complementarity. The smooth dynamics relax the complementarity condition, result in a surrogate model that is informative gradients but is biased. We obtain dynamic Jacobians and sensitivities with respect to the smoothing parameters by differentiating the KKT conditions of the SOCP. Using these sensitivities, we derive bounds showing that the non-smooth dynamics can be written as the smooth dynamics plus a bounded deviation term. Both are C1 continuous. This enables the use of trajectory optimization, and the deviation depends on the contact Jacobian. Collecting results, we represent the non-smooth dynamics as a continuous differential nominal model plus a bounded deviation, making the formulation amenable to trajectory optimization. Unlike the non-smooth dynamics alone, which linearization is only physically valid in the pushing direction and not in the pulling direction, our one-sided deviation term captures the unilateral nature of contact. Given this representation, we synthesize closed-loop reachable tubes consisting of a nominal trajectory and a set-valued rollout. We prove that the true non-smooth rollout remains within these analytical tubes under a linear feedback controller parameterized by nominal trajectory and causal gains. Rather than optimizing only the nominal trajectory, whose feasibility does not necessarily guarantee feasibility under the true dynamics, we optimize the closed reachable tubes of the non-smooth systems. This augments the original trajectory optimization problem with constraints on tube size and controller parameterization. Accounting for the true non-smooth dynamics can lead to qualitatively different behaviors. In one example, the baseline methods result in robot collision, where our approach guarantees collision-free. In another example, we require the manipulated objects to remain within the table. Although the baseline nominal trajectory satisfies the constraints, the true rollout violates the constraint, and our method instead guarantees the object remains within the table while reaching a state as close as possible to the goal. We also validate our method experimentally on hardware. Despite modest input-row discrepancy in object mass and control stiffness, the object state remains within the pre-computed analytical tubes. It demonstrates the correctness of the analytical tubes. Finally, we apply our method to a high degree of freedom system. We successfully compute reachable tubes and synthesize a linear controller for this high-dimensional system. Once again, the true rollouts remain inside the predicted tubes. We further evaluate the synthesized controller in the full simulator with varying mass and control stiffness values. The controller consistently computes the task of rotating a cube by 90 degrees, demonstrating the effectiveness of the synthesized linear controller. In conclusion, we enable a formal synthesis of controller through contact. If you have any questions, I'm happy to answer them at the poster session. Thank you.
And for the last talk of the session, we'll hear from Glenn Cho about parallel differentiable reachability.
Okay, cool. So we make reachability analysis fast and differentiable on the GPU to enable certified training and online planning with neural dynamics and controllers. So neural nets are great, right? But their performance can potentially degrade under uncertainty. To certify robustness under uncertainty, we typically can use reachability analysis. In reachability, we compute a worst-case set of reachable states and certify safety by making sure that they're all still safe. Ideally, we'd use reachability within the training pipeline to directly learn safe by design models. But today's reachability tools, unfortunately, are slow, post hoc, and offline, making them impractical for robotics. So our goal is to make reachability instead practical for learning and planning. So to achieve this, we redesigned reachability analysis as a differentiable and GPU parallel primitive that operates directly inside training and learning and planning pipelines. So our reachability tool, diffreach, certifies continuous time neural network control systems. So most existing reachability tools alternate between bounding the continuous time ODE and the neural components, which can lead to set representation incompatibilities that make the reachable sets blow up. So instead, what we do is we use Taylor models to bound the ODE and Crown to bound the neural components. But unlike past work, we design a unified interface between the two that preserves linear state dependencies without loosening bounds and alternating between during the alternation process between the two. Our tool's in JAX, it's on a GPU, and it's differentiable, which makes it great for downstream learning and planning. So next, we develop certified training methods for neural dynamics and controllers that use our reachability tool in the loop. So for training neural dynamics, we start off with just a standard L2 prediction loss that optimizes the nominal accuracy. But what's new here is that we also leverage our reachability engine to quickly calculate and penalize large reachable sets under uncertainty during the training loop. So this co-design of these models and certificates actually enables us to learn accurate models that are also going to be easy to verify downstream. So we also use our reachability tool to robustify online planning. So actions that are nominally safe might be unsafe under uncertainty, so our goal is to actually make certified safe actions under uncertainty. And the way that we do this is we use our reachability tool in the loop of a MPPI-based planner. So candidate actions are evaluated not just on their nominal task performance, but also on their worst case behavior according to their reachable set penalties, which discourages uncertainty growing behaviors. And because our reachability tool is differentiable and on the GPU, our planner can efficiently optimize these robust control policies. So to stress test our reachability tool, we evaluate on a tethered UAV system that has 72 state dimensions. In the middle, we show a sampling-based estimate of their true reachable set. On the right, we show what we actually compute. They're pretty similar, which is great because that shows that even in 72 dimensions, our solver runs really fast, 0.2 seconds, and kind of gives you something similar to the sampling-based certificate while giving a guarantee. We next evaluate a certified kind of neural dynamic stranding task on T-pushing. So the question is, does the reachability loss actually harm the prediction accuracy? The answer is no. We see that the true and the predicted sets look pretty similar, so in this case, there's no trade-off between the two. And that's really useful for planning, because we can evaluate reachability where MPPI with our certified neural dynamics model on this T-pushing insertion task, and compare it to vanilla MPC under uncertainty. And here, we kind of show that our method succeeds, whereas vanilla MPC fails, because vanilla MPC is too aggressive near the T-object boundaries, and that makes it really fragile under uncertainty and model error. Instead, a robust planner is basically more conservative, and so it takes safer actions by using reachability to forecast the worst-case outcomes. And that basically enables it to work zero-shot in the real world, where we perform robust closed-loop control under sim-to-real error at 5 to 10 hertz. So overall, we develop a general, parallel, and differentiable reachability tool and propose new certified robust training and planning pipelines using reachability in a loop. See you at the poster.
We then invite all the speakers to come to the stage and be ready for a Q&A session. Do we have questions?
Hi, I have a question from the second presenter, the failure recovery. From reaction to anticipation. Oh yeah, awesome. So my question is, what kind of failure did you consider in your task, and also further instances that it couldn't recover from the failures?
Sorry, excuse me, your voice is a little bit slow, yeah.
Oh, okay. My question is, what kind of failure did you consider? And also, could the recovery always happen, or it was sometimes that it didn't happen?
Yeah. Thank you for your question. Yeah, we mainly consider the disturbances from outside or some failures during the execution of the robots of itself. So for sure, the agents cannot anticipate all the failures, but we can anticipate most of the failures due to the capability of the LLMs. And also, we can evolve the agents. For example, if you see some failures, you can evolve from this failure and learn the failure in the next round of the execution. Yeah.
Okay, thank you.
Question to the second presenter on the information-driven planning. Second from the left.
Oh. Gotcha. Hey there.
You presented on the water or your surface vehicle. What exactly were you mapping there? What exactly was the observation in that example?
Thank you for the question. It was bathymetry. We had a single beam sonar mapping the distance to the surface, and using all the data from the vehicle throughout the mission, we were able to reconstruct how the underwater terrain changes.
Okay. So what if you had a single point measurement, things like salinity or temperature? Because then the observation is just a single point.
It's the same thing. It doesn't change.
But you seem to have a region of interest. Then the region of interest would be a single point.
So the region of interest is actually computed from how the data is correlated. So if you're looking at a smooth underwater terrain, sensing in the middle of this terrain is going to give you a good sense of how the whole curvature in that area is going to behave. So using that information, which is already encoded in the kernel function, we are able to say beforehand that, hey, I know how the data correlates, how the terrain changes. I'm going to measure at one point, and based on our theorem and the derivation, we're able to say, because you measured here, you don't have to measure every single point in this region. This region is done.
But there's always a kernel, basically. There is always a kernel to any measurement.
Exactly, yes.
Thanks, that's good.
Any other questions? Any other questions? So maybe I'll try asking one to Wangxi and Jingshuang Tang. So I'm actually curious on how sensitive is your method to like dust that might be on the wheels of your object.
Sorry, your voice is somehow low.
How sensitive is your method to disturbance or like dust on the wheel of your object?
This is ISO tool or a planar planner. So it isn't out of the scope of our research.
Okay, that's all right. Yeah, thanks. Any other question?
Don't be shy. We have probably time for one last question.
Okay, I'll ask another question. Okay, so I'll ask another question. So I'm actually curious with this first speaker, Wenzhen. Yeah, okay. So in your title, you mentioned QMDP. So is it QMDP or the full-blown POMDP?
It is based on QMDP, yes.
Okay. So.
Okay, then if there are there any more? It's hard to see. Somebody coming up.
Thanks. So this question is for the steerable needle planning with reachable.
Is this me?
I think it's your student.
Oh.
Yeah. This is about that shape query inside that medical robotics.
The shape library one?
Yeah, shape
Okay.
library one.
Yeah.
Cool, sorry. I should know that. Okay, so my question was, when you do a mapping of the shape distribution and then you pick a shape and then that goes into the dimensions, but when you're actually inserting it with the 6DOF, you have a deviation during the insertion when you're shifting from one shape to the other, right? So even if it reaches the shape accurately, the process of transitioning from one shape to the other can be extremely deviating on that passage. How do you control that?
Yeah, so that was kind of the issue that we observed. Once we have the sparse motion plan, then we have to kind of get from one shape to the next. And that's what the whole interpolation part tried to solve. So we show using our method that when we slurp between tip poses and linearly interpolate joint space, that does cause some deviation by itself, but we were able to exploit the radial symmetry of the continuum robot. And we can kind of use some tools from that symmetry to help minimize that deviation as we're transitioning from one shape to another. And the more interpolation steps that we do in between, the smaller we can bound that deviation.
So are you calculating the maximum deviation or overall deviation across the whole trajectory space? Because you're introducing new spaces as well.
Yeah, so the deviation that we calculate is after we align the shape to the path, and then we just kind of do a point-wise deviation calculation, and then we average that over all these steps in the entire motion plan to get the final number.
Okay, cool. All right, thanks.
Thank you.
Okay, with this we should finish the session. Thank you very much. Thanks for the speakers. Thanks for coming.
Thanks, everyone.
What you talking about? Was it something about your smile? I didn't even pay attention, 'cause I'm lost in